Pues muy bien, primero que nada, me gustaría agradecerles a todos su interés por el taller. También agradecer a los organizadores del consejo, ¿verdad? Y a nuestros organizadores estudiantiles, que, pues por supuesto, este taller está organizado por la SEBI, que es la Sociedad Estudiantil de Biotecnología y Bioingeniería de Yucatán, y también por la nueva Sociedad Estudiantil de Estadística y Data Science, o la SIDS, cuyas redes de estas dos asociaciones pueden encontrar en el chat. Ahora, un poquito para presentarnos, pues la segunda parte de este taller va a estar impartido por el doctor Gustavo Martinez, que pues es un postdoc en la Universidad de Dalhousie, en Canadá. Él pues tiene doctorado en biotecnología de la Universidad de Caxias do Sul en Brasil. Y pues actualmente trabaja mucho con inteligencia artificial, mayormente con biología computacional. Y pues su servidor, mi nombre es Pablo Camarnis Boldo. Soy ayudante de investigador SNI y más aquí en Yucatán. Y además soy el presidente fundador de la CITSE, que pues es una de las asociaciones organizadoras de este taller. A continuación vamos a cambiar a inglés. Me gustaría decirles que pues sus preguntas las pueden dejar en el chat. Pueden ser tanto en español o en inglés. También pueden levantar la manita en los espacios que vamos a ir dejando en el taller para sus dudas conforme vamos avanzando, sobre todo en la parte práctica. Y pues el doctor entiende muy bien el inglés, pero me parece que mayormente les vamos a estar contestando en inglés para mantener pues el tema del taller. Pues ya con esto, pasamos a la parte ya en materia. Vamos a pasar al inglés. So for the introduction, as you know, access to clean drinking water is both a necessity and a human right. Currently, 72% of the world's population has access to safely managed water. That means water that is treated, that has plumbing, but there are still almost 300 million, humans that don't have reliable water sources or that have unimproved water sources, and there are still 115 million who collect water directly from rivers, lakes, and other surface uh, sources. Because of this, it is essential to ensure that any water source, especially if it is untreated, comes from a basic service and is also safe to drink. Verifying that the water is potable and free from contaminants should always be a priority. So this chart shows the number of deaths linked to water sources, especially unsafe water sources. And as we can see, most of the deaths are happening in Africa and Asian countries, but there are still some countries in America that have also deaths related to water sources. So these deaths are preventable, and the diseases caused by water sources not only plague the health of these people, but also play an important burden on the global economy and the healthcare systems. Now let's talk about the concept of potable water, also known as drinking water. This is water that is considered to be safe for human consumption. It must meet several parameters, which can vary depending on the country's legislation. In addition to being safe, drinking water should always be palatable, meaning that it should have no flavor, no color, and also it should be odorless. Some of these parameters that determine water safety can be challenging to measure. either because they are expensive or require specific expertise. For example, testing for coliform microorganisms, which are organisms that cause gastrointestinal disease, can be a complex endeavor. So let's imagine that we are tasked with building a machine learning model that can quickly and cheaply predict whether a water source is potable or not. This would allow us to assess water safety efficiently without needing costly or specialized tests. To create this model, we need data. This is where the water quality dataset comes in. This tabular dataset includes information from various water sources around the world. Each source has been tested for several quick-to-measure safety markers, and we also know whether this water was deemed potable or not. Next, I will explain the variables that are included in this dataset. It is very important to understand the original meaning, uh, significance, and interaction between these variables so that we can correctly interpret the model that we are going to build. By knowing what each of these variables represent, uh, we will know that our model is both useful and it can be applied outside this environment. First up, as we saw, this dataset includes the pH of the observations. So pH, as you probably know, measures the activity of the hydrogen ions, and it is expressed on a scale from 0 to 14, where values close to 0 are acidic and values close to 14 are basic or alkaline. Most potable water sources have a pH between 6.5 and 8.5. pH is also important because it affects many other variables that are included in this dataset, and that makes it a very key factor in water quality. pH is influenced by the balance between carbon dioxide, carbonate, and bicarbonate. So for example, when CO2 is present, pH tends to drop, making the water more acidic. On the other hand, if water is in contact with limestone, such as in here in Yucatan, the pH tends to increase. So if the pH of water is acidic, the water becomes corrosive, and this can harm our organisms, but also it can be corrosive to water pipes and other metals, and the water may be contaminated with these metals. On the other hand, when water becomes alkaline, there tends to be um, flavor changes, which may change water palatability. And as I've said, this is considered as a factor when deciding if a water source is potable or not. Next up, we have some parameters that are related to the content of solutes in water. We have hardness, which is caused by calcium and magnesium salts. As we probably know, water here in Yucatan is very hard, meaning that water plumbing services tend to clog up with these salts. And while there's no health guideline for this parameter, meaning that there is no law or recommendation that determines a certain level of hardness, there are some changes that occur when water is too hard, mostly changes in palatability. So water tends to become very bitter or soap tasting when it's too hard. On the other hand, solids, which are measured in parts per million, is a measure of how many solids there are dissolved in water. Again, there is no health-based guideline for the total dissolved solids, but this parameter also changes flavor of water. Next, we have conductivity, which is measured in microsiemens per centimeter. And this is a measure of how well water will conduct electricity. And it depends on which ions and solids are dissolved in water. The World Health Organization specifies that the value of conductivity should not be higher than 400. But as we can see in the chart, some potable water sources in the US are as high as 1500. Next, we have turbidity, which is an optical property of water. So turbidity basically measures how murky the water is, as we can see in the image. And this is a much stricter legislation because no one wants to drink water that is yellowish or brownish. So we have the WHO recommended value is lower than 5 nephtalometric turbidity units, which are the units that we use to measure turbidity. Next up, we have chloramines and trihalomethanes, which are two of substances that appear as a result of water treatment with the intent of disinfecting water. So while the presence of these substances may indicate that the water has been treated for human consumption, it, there are also a certain degree uh, of, of permitted values. So for instance, chloramines, which are a result of the reaction between chlorine and ammonia, uh, should only be lower than 4 milligrams per liter or 4 parts per million. So if the value is higher, that could mean that the water was treated, but not for human consumption. For example, a swimming pool. So you should not be drinking water from the swimming pool, even though it has been treated. And trihalomethanes, well, this also comes from another way for treating water, mostly in Europe. And in this case, values should be lower than 80 parts per million. Finally, we have the organic carbon. So organic carbon is a measure of how many carbon derived or carbon containing molecules we have in water. These molecules mostly come from decaying organic matter. So the organic carbon is sort of a quick to measure a parameter of how much contaminants in water there are, which come from organic sources. This can include bacteria, ammonia, sorry, not ammonia because it doesn't contain carbon, but there are also some sources of carbon containing contaminants which are synthetic. So the total organic carbon or TOC should only be 25 parts per million, but this is the higher end of the spectrum. The legislation in the United States, for example, only allows for 4 parts per million. So it's very important that we keep in mind that the numbers contained in the water quality dataset are coded in a certain unit value, mostly parts per million, but also NTU units for turbidity, for example. And Although we have a wide range of values in this data set, we know for certain if a water source was either potable or not, that is coded in this variable potability, which is 0 for when the water is not potable and 1 for when the water was deemed potable. And we are going to use this data set to train our machine model, which comes in the part 2 of this workshop. So I will ask you now, is there any doubts about the variables included in this dataset? Well, if there are no doubts, then we should continue to, yeah, tell me.
Hi, good morning. I would like to ask how can you get this data using what kind of machine or what method?
So there are many methods that you can use to measure these variables. So obviously, pH you measure with a pH meter, which can be the pH strips, which change colors, or it could be something that you use in the lab. The important thing to understand is that all these data points can be collected quickly, such as in the case for the total dissolved solids. We use this little device, which is, as you can see in the image, it's very easy to use. You only dip it in the sample that you want to test. And the point of these variables is that they are very quick and easy to measure. So imagine that there's a community that lacks a safe water source, and you're trying to determine whether the river next door is has potable water. And you don't have a microbiologist at hand that can test whether this water is rid of any microorganisms that are harmful. But you have a set of tools that can quickly measure some of these parameters. So for each of these tests, we have different devices that can be measured, that can be used, sorry. Um, and speaking of the principle of these devices is outside of the scope of the workshop. But if you have any specific doubt about how we measure any of these uh, parameters, where you can ask, but as a broad answer, there are many instruments that we can use.
Okay, thank you so much. I have another question. These measures are taken every every time, like 10 minutes, 1 hour, 2 days. I would like to know if there are a time constantly of take measures.
No, these measures are supposed to be instantaneous, so to speak. So imagine you collect water in a beaker,
Mhm.
you take it to the lab or somewhere where you can measure all these parameters at once. And there's some nuance to this because there are some data points that don't contain all the variables. So for instance, there are some observations that have pH, solids, organic matter. They lack, for instance, conductivity.
Okay.
So in those cases, we assume that we didn't have the equipment necessary to get that reading. So it's blank. I will show you, for instance. As you can see in these are only like 8 data points from the data set. Next up, we will see how many readings there are in this data set. But as you can see, reading number 1 doesn't have a reading for pH. So we took the sample and we took it to the lab, but we didn't have the pH strips, for example. And for readings 2 and 3, we didn't have the what it takes to measure the sulfate content. I should also say that this data set comes from kaggle.com. If you're interested, I will share with you the original link for the data set, but we will have access to the whole data set in the next part of the workshop.
Okay, thank you.
Any other questions? All right, so I'm gonna leave you with Gustavo here. I will stop presenting. So remember, if you have any doubts during the workshop, you may leave it in the comment section, and I will help you if you need it with the translation of the questions. So it's up to you now, Gustavo.
All right, thank you so much for your great introduction, Paulo. So I'm going to take over now the second half of the workshop, in which Paulo will also be assisting us. We're going to actually have the hands-on practical work in how to analyze this brilliant data set that was described by Paulo, and we're going to apply some machine learning techniques. Again, if you well remember from one of the first slides that Paulo presented, what we're trying to do here is to create a predictor to say whether the water sample that we are dealing with is potable or not, based on all of these descriptors, all of these columns, such as pH, hardness, conductivity, turbidity, and so on, that Paulo has just described. Uh, I have here a short presentation that I'm going to keep returning to it back and forth, because we're going to have the notebook with the code that we're going to be working with, and we're also going to use the presentation here for some external material so I can add more context on it. Let me just see how I can share here my screen. Do you see my screen?
Yes, Gustavo.
Oh, thank you, Paulo. Okay, so this is a brief overview. Oh, sorry, guys, that it's in the wrong one. Yeah, I'll just leave it like that. That's fine. So just leaving, having you with a brief overview here about my work. I am currently a postdoc at Dalhousie University. The laboratory that I work for is focused on emerging infectious diseases. I'm a postdoc based on computational analysis. So that means that my whole academic trajectory has started with computer science, or what we used to call in Brazil computer information technology. Those are pretty much the same undergrad courses. And then, as you can see, I slowly transitioned from a computer centered formation to biology in the master's, biology in the PhD, again working with more biological concepts here in the postdoc. As I like to say, I create computational solutions for problems that are based on biology. I have here the QR code that should take you to my GitHub where I have most of my work presented there. So if you're interested, you can take a look there. And I know that we're probably not going to have too much time for it today, but if you have any particular questions about my research that I do, academic trajectory, I would be happy to answer these questions to you today, probably in a briefer manner, but you also have my contact information, and I think that we can exchange information even after the workshop. Shouldn't be a problem at all. Uh, Good. I would like to start here with more of a reflection on this whole concept of data science, artificial intelligence, machine learning. I was reading a book a couple of weeks ago. I can get you the name of the book later. I was actually reading Portuguese, so I don't exactly know the name of it in English or Spanish. But there was one passage on that book that really got me, and it says something that this is the actual the translation that I did myself. So the actual words were there in Portuguese, but whatever. So they said that having the monopoly of the most brilliant engineers does not mean having the best results. Then they had another passage and they concluded with saying that good AI depends on good data. So, what you're going to see here today, when Paulo and I started to idealize this course a couple of months ago, Paulo said, okay, we have this environmentalism idea that we should be applying some concepts of it. And that's why what we're going to do here with some data that talks about water quality. So you have the whole environmental idea of it, this type of chemistry. And when Paulo and I started to design these, Paulo said, okay, we might have something like 4 hours. So at that time, I already knew that in 4 hours, I could select only one of the topics that we're going to see today and go so deep into these topic that our 4 hours would be gone quite easily. So it wouldn't be a safe choice for me if I would be here with you today, me and Paulo, for 4 hours talking about one particular application, one particular algorithm that uses AI. On the contrary, I want to provide with a bird's eye view on what AI is and what type of problems you can solve using machine learning. And for that, you're going to plug your own data. And that's why I think that the data that you select to answer your questions using AI, using machine learning, is probably at the end of the day more important than the machine learning itself. You will see from what we're doing today how many people we have here with us. 12 people, including Paulo and myself. So we have 10 students who are attending here. You're going to see that the actual technical skills for you to do the machine learning, the AI part of something, there is nothing special about it. This is not quantum physics. Everyone can learn it. I don't know your background for the students that we have here. Maybe you can live here in the chat for us. What is your undergrad course? Because I know that when I talked to Paulo about it before, how we should expect the audience of today's course, Paulo mentioned that we might have people from different areas. So if you can just live here in the chat so I can have an idea about it, it will be really helpful. And this brings us to, again, this concept that the AI itself, the application that you're doing, it isn't the most complex part of what you're going to have. Your analysis can only be good if you have good data. And again, here we're working with data that is derived from an analysis on water potability, for instance. Uh, some of the data that I use in my work in the lab is related to clinical readings from patients that are undergoing infections from viruses. You might be working with a plethora of different applications on AI that uses different data sets. And again, if the data is not good, the AI, the machine learning itself probably doesn't have a lot to work with. So it would be perfect if at the same time we could have one person who is the best mathematician, the best programmer in the world, and this person would also have access to the best data that they can have. This would be the perfect, the most optimal scenario. But if you have to focus on one thing, I would tell you to focus on the quality of the data that you have. And this goes all about how you are collecting this data with your sensors that Paulo was describing here before. And actually getting to know your data. You need to understand the data that you are working with because this would be the best way that you can ask the appropriate questions on your data. So with this this little reflection here, we're going now to focus on the AI part of it itself. But always remember the AI is not complex. There isn't much intelligence on artificial intelligence. It's just a lot of data. So if you can drive your efforts to getting better data, to collecting better data, to getting to know your data, it is probably going to be more helpful to you at the end of the day than you actually knowing all the mathematical intricacies of the models that you're trying to execute. Very good. I think that we are good for now. Let me see if we have something here in the chat so I can check your backgrounds here. Okay, we have biotech, good. Renewable energy engineering, physics engineering, applied chemistry, mechatronic engineering, really good. So we have a diverse audience here. I'm going to get here the link that Paulo shared with us on the data set. Um, the bottom line is that you eventually will have to download this data set, but if I am not wrong, for you to download a data set on Kaggle, Kaggle is actually a very good source. You can find all different types of data that you want. You can, let's say here you want to have, oh, these are some of my past searches here. Brazil elections 2022. So I was working with some of the results that I had. So as you can see, you have all of this. This is really interesting. If you have time in the future, you can definitely start exploring it. But yeah, this is the water quality data that Paulo shared with us. However, probably for you to download the data set, you need to have an account and be logged in. So to save some time here, instead of asking you to actually download these and having to create an account on Kaggle, I'm going to share this link with you that is here in the chat. Please see if you can click on this link and access it. I tried to change the permissions before, so anyone with a link could have access to it. And I don't know if all of you here also have access to a Gmail account. This is going to be mandatory, okay, because the notebook that we're going to execute is actually executed on Google Colab. But I don't know if any of you are familiar with that, but you're going to need it. And probably for accessing the Google Drive link here with the data, you are also going to need a Google account. So uh, once you access it, the link that you have here, I would just ask you to download it. You can right click here. Sorry, my Google is in Portuguese, but you will go here in this option to download it. Then you'll have to download it to your local computer. So I'm going to allow you some moments when you do that. If anyone is having any issue, please let us know in the chat. Both Paulo and I are here to assist you with that. So please get the data downloaded to your computer. I see here that we have some people liking the comment. Maybe this is an indicator that you managed to get it open and also download it. And then if you download it, you can locally access the data on your computer as a CSV. CSV is generally the go-to standard for most of the data analysis that we're going to have. Sometimes you can also have things in Excel and XSLX format, but CSV is uh, the most commonly used. Also, if you're not aware of what CSV is, it stands for comma separated value. So if I open this here with my text edit, instead of opening with the spreadsheet viewer, you will see that all the values are separated by a comma. So this is a really good way for you to save space and in your disk when you're dealing with large instances of data. So as you can see here, comma separated values. Everything here is delimited by a comma. Okay, so are we set here with the download of the data? Is anyone facing any issues with that? I see that we have 7 people who like it. One of them is Paulo, who doesn't count. So let's say 6 students. Okay, 8. Now we're in 7. Okay, so good. All right. Once you downloaded the data, now we're going to open here our notebook environment. Again, I don't want to spend too much time here explaining what a notebook is to you. Basically, what you need to understand that this is basically the software that is executed on the web that is going to give us access to Python. Are you familiar with any sort of programming here? Um, Maybe the engineering students might be a bit more familiar with that. Does anyone here know how to program? You can please type in the chat. Okay, we have here the basics a little bit. Right. See more people are typing, but that's good. I'm not going to actually to require you to program in a high level today. Most of the things that we're going to see are pretty straightforward, pretty simple, and you're going to have access to all the notebooks that we have. I see here that one Liam has knows how to program in Python, C++. Victor is learning the basics of Python. This is really good. Yes, I'm a little bit biased, or as you guys like to say in Spanish, I have a sesgo. I learned the word sesgo in Spanish a couple of weeks ago, and I've been looking for all chances that I have to apply it. So, because I remember that you have riesgo and sesgo. I'm trying to use them both separately, but yeah, joke aside. So I have programmed in Python forever. Since I learned how to program. I started programming in C++, then I did some JavaScript, but then I got into Python and I'm still here today. So I have a CSGO on it. For me, Python is the best language. Uh, if you're then working with machine learning, I don't think that there is any doubt of it. If you're a general programmer, you can say Python is extremely slow compared to C++, to C Sharp, even JavaScript. But machine learning, there's basically nothing that you can do. You will eventually have to use Python. Um, I know that some people also like to use R. R is probably easier to understand than Python. So if you're entering in computer programming, maybe uh, a good way for you to start would be with R, and then you can transition to Python. But again, hardly ever you're going to be able to not to use Python as a programmer, especially if you're working with data science and machine learning. And all of these long talk here that I had in Python is to explain you now the concept of Google Colab. We're not being paid by Google, but this is basically a computer environment, a virtual computer environment that Google provides us for free, and you can have access to a Python notebook. The thing is that if you can have access to Python in your local computer, but uh, you will probably have a different variety of people. Some people use Windows, some people use Linux, some people use Macs. And then having to locally install Python in each one of your computers, we have 10 of you here. Uh, Paulo can correct me if I'm wrong, but we would spend the whole time of the workshop today only to get Python installed in your computers locally. So that's why we can make use of an external device. This is basically a computer that is running on the cloud that Google is providing to us. It is limited because we're not paying for it. If you have the needs to have some more computing capacity, then you can use the paid versions of Google Colab, but it should be more than enough for the analysis that we need to do here today. So I'm going to ask you to open this website here as I am already logged in my Gmail account. It shows all the past notebooks that I've been working with. So you just type here on Google, which is Google Colab. Let me get the link for you here in the chat in case you missed it. Just open it. If you have an active Gmail account in your browser, you should have something like that. And then I'll ask you to click here on new notebook because we're going to start one here from scratch with all the analysis that we need. When you do that, you should have a screen that looks a bit like that. I prefer to use the 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 dark mode, so yours might be a little bit different than mine, but shouldn't be too away from what you have here. Oh, that's a good way to get them interacting, Paulo. Like if you're able to access it, that's smart. Okay, we have here one like. I know that things might go a little bit slower right now because we need to make sure that everyone has their environment already set up. But you see, after we have it all up and running, we'll just start coding and talking about the analysis that we see. We have 7 likes and someone is typing. Let's just make sure that we have no hurdles here. Eight likes right now. And here you can see the details of your virtual machine. Your resources. You have memory, you have disk. See, they give us 12 gigs of free RAM, which is really good, and 107 gigs of disk. And I think that they use 4-core CPUs. I'm not entirely sure. Okay, I saw that someone was typing and then just stopped. Maybe you figured that out. So I assume that everyone right now has Colab already open with the new notebook. Uh, I already clicked it here on mine, but you see where I have here this RAM and disk that shows this small plots. You should have a button here that says connect. Also, go ahead and click on it so you can have your notebook connected. As you can see, we're connected to Python 3, Google Compute Engine backend. Then we have the information on RAM memory and disk that we analyzed it before. So by clicking connect here, there you should have a button here that says connect. At any time, if you're not following us, please type in a chat, open your mic. You can ask in Spanish. I understand Spanish. I'm just not very good at speaking it, especially in these technical things that I have never learned in Spanish. So don't be shy. It is really important that all of us have access to it and be at the same stage. You also have Gemini, which is basically Google's Chat GPT. It's really helpful. I'm not going to lie, I use it all the time. It really helps me to program. But if you don't know what you're doing, then I would say it's not the best way to get you learning new things. It's good to do the hard work, but if you're learning something new, it's better to stick to the old traditional methods. Okay, so I'm going to assume that everyone has access to it right now. Now there's one more step that you're going to have to do in order for you to get the workshop rolling here with us. And for that, you're going to click here in this icon that has a folder, which says files. You're going to go here and you're going to click on it. It will open the side panel and you will see that you have this third icon here on your top left corner that says Mount Drive. So there is one limitation. You're going to click on it, okay? It will take some time for it to mount because it's going to connect to your Google Drive. For sure, you need to permit it to access your Google Drive files. So I'm just going to allow the access to it, and now it says here that it's mounting. It will take a few seconds to get it mounted, depending on the volume of your Google Drive that you have. The longer it should take. And why Google does that? This is, in my opinion, one limitation because again, we're using something here that is for free, so Google does everything that they can in order to integrate all of their platforms. So in order for you to access data and these data be analyzed in your Google Colab environment, that data needs to be uploaded in your Google Drive. Let's say that you downloaded something locally on your computer and you want to use those data points that you have locally in your computer, first you need to upload them to your Google Drive, and then Google Colab will have access to it, which sometimes is a bit of a terrible and very limiting factor, because if you have too much data, you will have to upload all of that to your Google Drive, and that might take forever. Here, we're working with a very small data set, so it shouldn't be a problem. So we're only doing that um, for uh, didactic purposes, I would say. So after you mounted Google Drive, now it comes the part in which you have to upload the data that you have just downloaded from the link that I sent you here, and you need to upload to your Google Drive. There are many ways for you to do that. You can externally open your Google Drive, go here to your Google Drive, and then you upload the data. But in order to cut it short, we can upload directly from the browser window here that is showing you Google Colab. So for that, you should click here on Drive. Sometimes it doesn't show it here, the Drive folder. You just have to refresh it, and then it suddenly should pop it here. So you just click on Drive, and then you click on My Drive. It will take a while depending on all the files, all the different folders and directories that you have on your drive. Here is my Google Drive with all the things that I have on it. Um, we want to keep it organized and not to create a mess in your Google Drive. So let's create a folder. You're going to here and right click under My Drive and create a new folder. And you're going to say here water quality. You can name it whatever you want, okay? This actually doesn't matter too much. So I'm just going to create a new folder. And in this new folder, I'm going to upload the data set that we downloaded, the water quality. So as you can see here, I have the water quality. You have different ways to upload the data. I am just going to open my downloads, drag and drop the water quality dataset on top of my newly created folder here, water quality. Okay, it just gives you a warning. The runtime files will be deleted. Okay, I understand it. And as you can see here now, uh, it is uploaded to your Google Drive. This is really important that you have up and running on your machines. So please go ahead and get it done. I think that we can have another message here, like if you were able to upload. And this will be the last step. After that, we're only going to do the coding part of it. You can also explore the data here. If you double click it, it should open a side panel with the data that we had already seen before. Thank you, Paulo. I want to have more space here in my work environment, so we're going to leave it out. One person here who uploaded, Alan. Good job, Alan. Okay, 3 people managed to upload. If you couldn't figure out the drag and drop, you can also double click here and just click on upload. And then you just go to your downloads, whatever you save it, your downloaded data. If it's in your desktop or in your downloads, wherever that might be. I have 4 people who managed to upload it. 5 people right now. Okay, see that we have 9. 9 in the meeting, 9 students plus Paulo and I. Okay. So we have 6, missing 3. Please let us know if you found any problems. Okay, 7 right now. Thank you, Paulo. And it's really important that everyone has this steps completed. From now on, we will have more freedom on how to execute things, but setting up the collab, mounting the Google Drive, uploading the water data set. This is imperative. You basically cannot do the analysis if you don't have this. Okay, if no one is saying a thing, I'm going to assume that everyone is with us. Or should we start comparing the lists here just to see who is not having access? Okay, so I'm going to continue. If you are facing any challenges, feel free to ask us questions, to interrupt us. Okay, that won't be a problem. Again, you can speak in or type in Spanish. That we will be able to get it done. All right. So again, I don't want to have here a computer programming class in which I'm going to teach you the concepts on Python. This is not the scope of what we design it, and we probably wouldn't have time for that as well. So we're going to have here these cells that you can see. This is the only thing that you have in your environment right now. And this is where you're going to write your code. After you write all of the code that you wanted for one cell, you're going to click here in this play button or Control Command Enter, and then you're going to execute that cell. This is basically how it is. So one cell has to be executed in order for it to work. So it's also really important that you execute them in a sequential order, because sometimes you've missed something and you didn't execute the previous cell, the next cell is not going to work. So there are different ways to program that people, we had here some students who told us that you were having some content with programming, Python, C++, for chemoinformatics and so on. So every programmer is different. So maybe the things that I say here to you, the way that I used to program might not be the one that you are used to program, but this is totally fine. We can have different ways to solving the same problem. So I always like to start here with documentation. I think that your code needs to be as documented as it can be. And for that, you're going to use here the text cells in Colab. This can help you a lot. You can also comment, but as you're not working directly with the raw.py Python files, we can have this interactive way of documenting our code. So whenever you're going to create a new cell, you can create a new cell of code or a new cell of text. Text is just for you to document and know what you're doing. Code is actually what is going to get executed. So we are going to have here our first cell, and I like to have it here for importing all the modules. You see, Python is gigantic. You have models for everything in Python. I saw here that some people said that you were learning Python because of chemoinformatics. You can learn Python for applying machine learning, statistics, very different things. So whenever you want to use particular parts of Python, you need to import these modules. Otherwise, if Python enabled us every single module that exists for it, it would take forever only for us to load the initial executor of Python. So that's why when we need to use something external that doesn't come packed with the Python software that you download in your local machine, or in that case is downloaded for us in Google's Python 3 compute engine backend. Python is already downloaded there. We need to apply these external modules in order for us to have access to their functions. Try to see a module as something that executes a function. Let's say that you want to create a plot of something. You need to apply a plot function. What is going to execute the plot function is a plot module that you need to load to your Python before you use it. Otherwise, if they wanted to enable all the Python modules at start, it will take forever. You will need a lot of computational power for you to execute that. So we're going to start here with a very simple module, which is called pandas, as the bear, the panda bear. So we're going to type here import pandas, and that's it. You can also give an alias to the name of the module that you are importing. So pandas is if you Google it here, pandas, Python. This is a library, a module that is used to do data analysis. So as you can see here, Python data analysis library. This is what Pandas is about. You have all of its documentation, the latest version, 2.2.3. And then on Pandas, you're going to be able to execute a lot of functions that are going to allow you to do your data analysis, data manipulation, and so on. It's always interesting for you to check the documentation, the references or something, so you have access to it. So we're going to here import pandas, and something really common that a lot of people do here when importing pandas, because we're going to have to type pandas a lot whenever you want to execute a function that is included here in the pandas module, the pandas library. You need to say pandas dot something, pandas dot read CSV, pandas dot something like that. Instead of that, we can give a nickname to it. So I can say here import pandas as PD. It doesn't need to be necessarily SPD. Import pandas as my library, whatever. It can be something like that, but just have in mind that every time that you're going to type does, you're going to have to type my library, whatever, which is not doing you any good in reducing the amount of words that you're actually typing. So I'm just going to have here import pandas as PD. So I'm going to create here a text cell, and I'm going to say here modules. So we have it separated, and now I know that in this cell, this is where I have all the modules. Now you need to execute this because you're telling to your Python, hey Python, please import pandas, and you can give it a nickname as PD. Execute it. As you can see, it will take 0 seconds. This will be quite fast, and you should have the green check mark here. So this is the first thing that you need to do. Just go ahead in your cell, type this, import pandas SPD. I have the complete notebook that I'm going to enable it to you as well, probably later at the end of the course, because I don't want you to keep copying things from there to this notebook. I want to be as interactive as we can, so we're actually doing things together. So once you imported pandas as PD, you can now use the functions of this new module that you imported. So I'm going to now create a new cell of code, and now we're going to do what we refer to as data importation, loading and exploring the data. I like to have it documented, so we have it separated from part to part. And now we're going to use the first function of the newly imported module called PD or pandas. So for that, I need to have a variable. Let's say that this is data, and I'm going to use the function pd.read CSV. Open close parenthesis. And now you're going to go to your folder that you created, that you uploaded your data. Here I refer to it as water quality. And you're going to go here in the water potability.csv. You're going to double click it, and you just go in copy path. Oh, good. Thank you, Paulo. So you go here, water potability, copy path, and you just paste this here inside of the brackets of pd.readcsv. It needs to be between single quotes. Okay, so don't forget about it. If you do not use the quotes, it is not going to work. So you need to specify the path of the file that you just copied, and now you have it here. Now, if I execute this cell, you will see the green sign again, and this should be good to go. So I see here that 3 people were able to import the pandas library. 4 people. 5 people. I cannot actually share the code of this with you in the chat because it is different based on the folder structure that you have in your Google Drive. So if you created the same folder name at water quality, then this should work. All right, now you can start exploring your data. So for that, I'm going to create a new cell so we can keep things separated. So let's go here, data.head, and you execute it. What is this showing to us? The first 5 rows of my data and all of its columns, right? We have 1, 2, 3, 4, 5, 6, 7, 8 columns plus potability. So data.head, again, it only shows you the head of your data set. You can explore this. You can visualize the columns that you have in your data. You just type data.columns, and then you have all the columns such as pH, hardness, solids, chloramine, sulfate, and so on. So all of these initial steps that we do, data.head that we checked before, data.columns, it's important for us to get to know our data. Remember when I told you that the most important thing on any machine learning type of analysis is the actual data that you have. So you need to be able to understand how your data looks like. There is another function here which is called data.shape, and you don't need the brackets on here on data.shape, and it's telling you 3,276 rows and 10 columns. Okay, it's always rows first, columns later. So this is the actual size of the data set that you have. If you go here and you just visualize data, it is telling you the same information, 3,276 rows and 10 columns. Okay, but this is showing you the first 5 and the last 5 as well, the heads and tails. Oh, good. That was really helpful. Thank you, Paulo. And you can even go further on that in getting to understand your data. There is another command here, which is data.info, and for that you need the brackets as well because you're executing that function. And this is telling you information about each one of your columns. You have here the number, the index of the column. You have the actual name of it, and this is really interesting because as Paulo mentioned that to us before, and if you execute here data.head again, you're going to see that you have some missing values here in pH, also in sulfate. And you can see here that in pH, I have 2,786 non-null, meaning that I have a total of, let's see here, I have 3,276 minus this, which is, it actually works as a calculator. Okay, so any arithmetic expression, you can just type it here and it will execute. So you see here that on pH, you have 491 missing values. This is, in my opinion, the worst fear of a data scientist, which is the missing values. It's terrible. We have to find a way to work with that, but we'll do that in a way. Okay, and you see that we have some other columns here that we also have some missing values, which is sulfates and trihalomethanes. Good. So let me exclude this cell here. There is another command that you can do here to get to know your data, which is data.describe. But I think that we need to have as a transpose. Yeah, data. Oh, sorry. Yeah, let me execute this data.describe dot t. You see here, it already showed you the results of data.info. So just scroll down. And this is really interesting because it is already doing some exploratory data analysis. This is a step that people refer to as EDA. Oh, just a question. Are you able to see my screen properly? Is the zoom okay? Do you need me to maybe zoom closer?
It's okay for me.
Okay, good. Yeah, we can always zoom in if you need it. That shouldn't be a problem. So we have here this tab which is called exploratory data analysis, in which you can start having some statistics, some very basic statistics on each one of the columns that you have. So for example, here on pH, I have the mean, I have the standard deviation, I have the minimum value, which is zero, as we have missing values for pH. Then we have all the 25, 50, and 75% quartiles of your data, and then you have the maximum. So this is really interesting that you can start exploring your data based on all the columns. So it can give you some ideas on it. So this is really helpful for a professional that we refer to as the expert of domain, which is the person who is actually proposing the research questions that you can have on these data. And right now that we have AI being present in everywhere, you can click here in this button here that says like a plot, and this is already creating some plots for you automatically. You're going to see that it actually requires a lot of code for us to create plots. I'm going to show you that later, but it's good to see that as AI is now part of everything and is being integrated everywhere, you can have it. Um, what did I do here? Anyways, that's fine. Uh, okay, so you have the plots that we did the exploratory data analysis. Now we're going to actually start doing some more analysis, and especially a process that we refer to as data preparation. And this is going to be really important. Let me add here a text cell. So data pre-processing, data preparation. And some people like to say that the data scientist, if you work with that, you're probably going to spend more time doing data pre-processing, which is cleaning your data, finding a way on how to deal with the missing values that you have, as we discussed about it before. We calculated for pH. So you need to find a way that whenever you execute your machine learning model on your data looks as clean as it can be. So we need to find a way to address it. Let me. What happened to my mouse? Yeah, now it's back. Okay, so let's go here and start doing some data pre-processing. Is everyone following me? Anyone having any troubles? Do you require any additional assistance from both Paulo or myself?
Sorry, I missed this part. How can I get the graphs?
Okay, so let me execute this again. You can erase all of that, and you just go here and execute this line of code, data.describe. .tt is because we wanted it as a transposed matrix. So you execute it, and then you see this button here on the very right side of the table that came out of these. Then you just click here, suggest charts, and then it will automatically produce the charts for you.
Thank you. I didn't saw that.
No, that's fine. Please let us know if you have any other questions. Okay, guys. Let's move ahead, and now I want to start doing some analysis here. With you, if you type data and you open the square brackets, this is something that in pandas we do to check individual columns. Let's see here. Can someone name me a column from our data set? Let's get here sulfate. Okay. I open square brackets. Between single quotes, I have sulfates. It is basically going to show us all of this individual column, data sulfate. And if we get here data potability, it is going to show us this individual column instead of showing the whole thing. So this is in pandas how we isolate one individual column. And it's really important because we can do some operations with one single column. Let's see here. So you know that potability is either 0 or 1. So it means that that water sample that we tested is potable if it's 1 or non-potable if it's 0. So this is in data science, in machine learning, what we call the label, the class of the data, what it actually is. Because if you see here, I have all of these 9 columns, pH, hardness, solids, up until turbidity, and then we want to determine whether our sample is potable or not based on the complex nonlinear relationship between all of these 9 columns. And this is one of the good reasons for us to apply machine learning, because if you have to resort to the relationship between 9 variables, you're talking about a 9-dimensional space, and checking how one variable influences the other. If you do that by simple statistical methods, that can scale out of control pretty quickly. So that's why you need a robust mathematical machine learning tool for you to execute that. So you can have that working for your analysis. So always remember the label is the binary class, 1 or 0, okay? When I check here, I have 3,276 rows and just one column, but let's say that I want to count how many ones I have and how many zeros I have. So you go here, data potability dot values, value counts. Sometimes Google Colab already suggests the Python function for you, and this is really good as well. So as you can see here, I executed data potability.value counts, and you see that I have 1,998 non-potable water samples, and I have 1,278 potable water samples. In the perfect scenario, you would have balanced classes, 1, 1, 1, 0. So we have here, what is the total size of it? 3,276 divided by 2. This would be the perfect scenario that sometimes doesn't happen in real life. We should have 1,638 potable water samples and 1,638 non-potable water samples. But that's fine. We can always work with unbalanced data sets as well, and this is not going to be a problem. Let's say now that you want to do something more interesting with that. Let's say that you need to have a plot on the ones and zeros, the potable and non-potable water samples that you have in your data. You can do that easily in a Python environment. You don't need to get these values, maybe open an Excel spreadsheet, and then you plot it. for that, we're going to use another module, another library, which is for us to plot. Import matplotlib.plt and sorry, .pyplot as plt, and you are also going to import Seaborn as SNS. Let me get this for you here in the chat so you don't have to copy all of that again. So these now are two libraries, two Python modules that we are going to use for plotting, okay? That's why I needed to include this additionally to the pandas that we already have, meaning that we're going to re-execute the cell that has all of our models. So matplotlib and Seaborn are now loaded, okay? Just go up above to your modules cell, copy that, execute, and you should be good. Now we're going to plot here the number of ones and zeros that we have for water potability. I see here that Paulo is probably asking if you. Oh yeah, that was good, Paulo. Don't forget to execute the cell with the modules. Okay, so for that we're going to have a SNS object, and we're going to do a count plot. Okay, this is basically a histogram, a plot of counts. So in my X, we're going to plot the potability, and the origin of this, the data, is data that I call data here when I import it from the Google Drive, okay? If I had named this data set, it wouldn't be a problem, okay? You can name it whatever you would like. Okay, so you execute these, and you also need the plt.show. And you should have here a plot with your counts for potable and non-potable. As you can see here, this is a count plot. You have here the 1,278 ones and almost 2,000 zeros. There are many different ways that you can customize this plot. You could change the color, you could change everything that you wanted. Actually, matplotlib in Python is a great way for you to make good looking plots. For sure, we're not going to spend too much time with that. Because we could easily spend the whole day just talking about it. This is one good instance for you to use AI models such as ChatGPT. If you just wanted to, have one color for ones and another color for zeros, maybe you could just copy the code that you have here and ask ChatGPT. Let's do that. I can actually do that. Okay, can you plot the data which has 1 and 0 in different colors? Let's see. Okay, it is giving us the explanation. So we just add, I could copy everything. Let's copy everything here. And let's go back to Colab. So 0 is going to be sky blue, and 1 is going to be light green. This is good because this is the part that I told you that when you do something like that, you actually need to know your code. You see you have here the palat. So this is the argument, the parameter that you're feeding to your count plot method, and then you're adding the color. So just do not do any blind type of AI application and use of these large language models, because then you're not actually learning. But if you know what is actually being done here, I don't see that as a problem in order for you to do things faster and having maybe even better plots. Oh, okay, we have a problem. ChatGPT was wrong. Okay. Testing without assigning you is deprecated. Okay, I don't want to spend too much time trying to fix that, but as you can see, ChatGPT is not always right. Maybe this is the issue. Maybe it's not counting that as a number. Let me just see here if this will work. Yeah, now it did. You just had to get the numbers ones and zeros in between quotes because they were not actually numbers. So in this is not only Python, most all of the programming languages, when you specify something in between single or double quotes, I saw that Paulo also said that for double quotes, it also works. I have always used it single quotes and I kept using that, but both are the same. Whenever you type something here, it is actually going to be a string, um, a vector of characters. And if you don't use the quotes, this is actually a variable or a number. So it is different in computer programming if I say this, one without quotes, then I say one with quotes, because one with quotes, I am actually dealing with a string that has the look of a number one. But if I want to work with the mathematical properties of the number one, I need to use it without quotes. So I know that it's a bit hard to wrap around your mind around these two concepts of ones and ones. Uh, if you want to get more details on it, you see you go here 1 plus 1, it is 2. And now you go here 1 plus 1. See, it's 11 because it's just concatenating these two strings. So this is the fastest way that I can explain that without getting too much out of scope. So when you're executing this code here that we got from ChatGPT, you just need to replace the ones and zeros without quotes to containing quotes. Okay, so we have an idea on how our data is distributed. You can even go ahead and do some other simple statistical analysis on your data. Let's create here another cell. Let's try to have maybe a correlation plot. You want to see how each one of the variables is or isn't affecting positive or negatively the others. So we're going to have here another plot, which is we're going to plot a figure. We need to specify the figure size. So figure size, what is that? How did it know that I wanted to do a correlation? Maybe because I already have this on my on another notebook, but wow, this is impressive. Yeah, data core, heat map, yeah. Wow, I'm impressed. So this is the correlation. Let me get the code here for you in the chat as well, in case if you need it. You don't want to type it all. And what we see here, we have a correlation between each one of our variables. For sure, this is not even close to the mathematical complexity that we have in machine learning, but we can start maybe getting some initial inferences on our data. You have here the main diagonal, which is always going to be 1, a positive correlation because you're comparing the variable with each other and it is always going to be the highest correlation because the numbers are actually the same. So you can just ignore that. And then you can start seeing that there isn't much correlation. You just by exploring the colors here on your heat map, maybe the 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 stronger correlation that you have is, can someone help me here? I don't see anything. Maybe this 0.17 negative that we have here in sulfate with solids. So what does that mean? If I have, this is a terrible correlation. Okay, correlation goes between +1 and -1, meaning that if I have a positive correlation, so it is a correlation coefficient that gets close to +1, these two variables are positively correlated. One goes up, the other goes up as well. On the other hand, if you have negative correlation, it means that one goes up, the other goes down. So here we have a bad correlation. It is the best one that we have in this data, but is still not good, meaning that when sulfate goes down, solids go up. They are negatively correlated, but again, 0.17, it is a very, very weak correlation. If we had something minus 0.7, minus 0.8, then we could be talking about something, but 0.17, that's neglectable. But still, you have a way here to start exploring your data. Okay, so let me do the job now and ask if everyone has managed to plot the correlation heat map. Let me. Okay, we have here Jose Manuel who managed. Thank you, Jimena. Thank you, Paulo. Ricardo did it. Liam, okay. Okay, perfect. So I think that everyone is at a good stage. Okay, so these steps that we were doing here right now, exploring data and so on, somehow they can be classified at the EDA that I mentioned to you before, the exploratory data analysis, because we're just doing simple statistical analysis to get to know our data, to understand it better. And if we have here columns, you have columns that are not correlated between themselves, this is maybe a good idea to try to apply some machine learning on it in order to predict. Because it's not the thing that I can say here that, let's say that I had a very strong correlation between potability and, I don't know, organic carbon, okay? So for me to predict something in that case would be really easy, right? Let's say that I had a positive correlation between potability and organic carbon. So I just check at my sample. If I have too much organic carbon, that is going to be potable. Otherwise, it's not going to be potable. This would be a very simple statistical analysis. However, what we want to do is machine learning in order to find the hidden patterns that at least the human eye is not able to see when looking at this data, because we need to find the relationship between turbidity, trihalomethanes, organic carbon, conductivity. So we have too many variables to keep track at the same time that it becomes complicated if we don't apply a robust mathematical model for it. That's why we're going to use machine. So let's continue here. We're now going to have to focus on our missing values. As I mentioned before, NA's missing values is one of the worst enemy of the data scientist. However, this is a clear reflection of the real world. You are always going to have malfunctioning sensors. You're always going to have logistical problems that are not going to allow you to get all the scope, the amount of variables that you needed for that particular data type. So you're going to have missing values. For that, we can start exploring our data here in the is null function. So you're going to check if you only execute here data dot is null, it is going to return you a table, the same table of your data with values true and false for each one of your cells. It's true because it has a new value here on row 0 for pH. The same thing that we found for sulfate, right? Row 1 for sulfate is null. However, this table is not very user-friendly because you're only seeing the first 5 rows and the last 5 rows. So if you just add here sum, you're going to sum the number of is null, which are true, in each one of the columns that you have. So we see here that I have 3 columns that have null values on them: pH, sulfate, and triallomethanes. So these are probably the columns that we need to fix and try to find a way um, to bypass, to work around these missing values. Because uh, if I try to use these for executing the machine learning, you will see that some models are just not going to accept null values. They don't know how to proceed when you have a missing value. And don't get me wrong, missing value is not 0. It's totally different for me to say that my pH is 0, then my pH is missing, is null. Null means that I don't have an observation for that. 0 pH means something. 0 sulfate means something. So these are totally different. Sometimes I've seen people getting their data sheet, and whenever you have here the null values, you just go here and type 0. You just go here and type 0. It is going to work in the machine learning algorithm. The model that you're applying, it is going to accept, because if you have missing values, most models are not even going to accept. Okay, it is not going to execute. It will return you an error message. But if you just go here and add 0, this is data manipulation in a terrible way. So never do such a thing. This is lying, this is unethical, this is terrible. Okay, so please, we're going to find ways to make data imputation, but following at least some of the reality that we have in the data. Okay, uh, you can even go further and have a plot here. What is the missing number dot matrix? MSNO, the missing numbers, and go here plt.show. And now instead of, oh, I forgot to import the library, sorry. Import missing no SMSNO. Oh, please execute this import here. Don't forget to rerun the cell with the modules, okay? And now we have the missing values matrix. This is visually really interesting because you can see the white stripes here. Each one of them, it is going to represent a missing value. And then you have all the columns of your data here. If you see from what we had below, thiallomethanes is the one that had the least amount of missing values. As you can see, the predominance of these white stripes here is less in comparison to sulfate, which probably has more, and pH, which is in the middle. Yeah, these numbers confirm if you see here. Yeah, thank you, Paulo. Remember to import the library, okay? You go up here, import missing no as ms and o. Okay. So now that we identified that you have data with missing values in 3 columns, we need to find a way to work around with that. And for this, there are going to be several different methods that you can use to apply. You can do one method that people refer to as the forward or backward fill. Let's open the spreadsheet here again, in which they just copy the last or the next existing value that they have. So for instance, here I had sulfate. I have a missing value here. I would just copy this value here. I would just copy this value here. I would just copy this value here. This is one way that people have to work with missing data. And again, missing data, they represent data that wasn't collected. So it doesn't matter how you look at it, the angle that you look at it, but there's always going to be some fabrication, okay? That data is not real. We just need to find something to include there so our machine learning can execute. So the bottom line is that data imputation is a very sensitive topic. You see, it is always going to, it's not going to solve all of the problems that you have at once. Okay, so if you do the backward forward field that I've just showed you here how to do, you can find good ways, a good narrative to support the execution of such method, but at the same time, you're going to find bad applications for you to execute such a method. So that's totally up to you. You have many different ways. One way that I would like to apply here with you for missing data, for handling the missing data, is what we call the mean of the class. Because you see here how many classes I have in my data. I have the class non-potable, and I have the class potable, the ones here. So I can create a mean for all the sulfates that are from the non-potable class instances, and I can create another mean, an average for the sulfate value in the potable water class instances. Again, this will have several problems, but we eventually need to find a way to work around our missing data. So the one that I selected to show here to you today, it is going to be the mean based, the class mean based data imputation. So we're going to to apply that. But again, please have restrictions for it, because you are, at the end of the day, you are creating data, okay? So be careful with it. For us to perform this, I'm going to have the code here for you. We get it here, yeah. So you just execute this 3 lines of code, and this should do the work for us. What am I doing here? First, I am selecting the columns that I want to fill, and I'm getting here pH, sulfate, and trialomethanes. And then for each column, I am grouping by the potability, so the class, potable, non-potable. And then I am adding the mean of that entire class. So you execute these, and now how can we check if we actually we imputed the data? Let's have another execution of the missing numbers matrix. So I'm going to create another code See how the matrix is looking here? Now I updated my data set, and you see that the matrix has no missing data at all. So I imputed data based on the mean. Again, always have the restrictions with that, because at the end of the day, you are just creating data that doesn't exist. There's no better way to describe that. I see here that Paulo is probably asking if you manage to.
I have a
Yeah,
question.
go ahead.
Okay, I wanted to ask if you can repeat like very quickly what was the trick that we applied, like we just applied to fill the missing values.
Yeah. So the trick, the method that we use it here to handle our missing values is, I get here the two classes that I have. One is 1 for potable, one is 0 for non-potable. And then I created an average for each one of the columns per class. So I have here sulfate. This is one of the columns that I have missing values. So whenever I have a missing value here in sulfate, for instance, this one, okay, I have a missing value here that is a 0. So the value that I'm going to input here, it is going to be the average of all the sulfate values that I have in my non-potable class. That's pretty much what we did here. We can go ahead and now explore. What did I do? Explore the data again, because this is now already filled. And if you remember, pH, before I did the imputation, it was missing here in the first row. Now I have here the value 7.08. This 7.08, it is going to be the mean for pH in my 0 class, in my non-potable class. So this is pretty much how we managed to include the missing data. Did I answer a question?
Yeah, thank you.
Okay, good. But again, remember, you are at the end of the day fabricating data, and you need to have this in mind. Okay, I see here. Yeah, you should see a clean missing number matrix after this. So this is how your matrix should look like. It looked like this before, and after I did the imputation, I have my matrix looking like this. We have 4 people who were able to deal with it. Six people. You have the code here. Just copy this code to a cell, execute it. But again, you're doing more than just executing code in a cell here. You actually need to understand all the things that we have. So I would be happy to handle as many questions as we could, even though that these questions would cause us not to do any other new code from now on. But my point here is that you really need to understand the purpose of the analysis. Everyone can copy code from one place to another. Okay, we have 7 here. Looks like 7 is the go-to number. All right, now we are going to create, let me create a text here, because this is going to be the data prep step. Now we're getting closer and closer to the actual execution of the the machine learning algorithms. And here I want to go through these with you in a way. Let me just copy this, because this is from the other notebook that I had, and I think that this can help you understand. So take a look at this sentence, this short passage that I have here. Data preparation for classification with machine learning. We first need to determine X and Y. I don't know how well versed you guys are here in mathematics, but we are trying to say that a function, f of x, is equal to y. Now, if you're not that familiar with mathematics, in non-mathematical language, we have a combination of x features, and these are the columns such as pH, hardness, solids, all of the 9 columns that we have in our data set. And we want to use a combination, the nonlinear relationship on these features to determine the Y class, which is potability, potable or not, 1 or 0. So basically, you're arranging your values, your 9 columns, and you're trying to use any information that you have there in order to predict whether you have a water sample that is potable or isn't potable. The great idea of it is something like that. You're trying to create a function to predict something. The function is the machine. The X element of your function is going to be your descriptors, the columns that you have, and the Y of your function, it is going to be the class that you're predicting. This is a good way for us to start dealing with machine learning. So you always have the X and the Y. The Y, it is always going to be the label, what you want to predict. And the X, it is going to be the elements that you use to predict Y. So for that, we need to get our data here and divide it into X and Y. You already know that Y, it is going to be the last column that we have, which is potability. So let's get here. By convention, several of the instances that I saw, that I learned with other people using machine learning in Python, they always refer to the X with capital X, okay? But this doesn't change anything. This is just a convention. So we're going to get here data.drop, potability, and we need to specify the axis. So what am I doing here? I am getting all the columns of data, and I am dropping only one column, which is potability, because potability does not belong to X. Potability, it is going to be Y. So you execute that, and you can actually visualize your X. See, I executed the X, and now stops at turbidity. It doesn't have the last column, which is the label, the Y potability. So you saw it work, and now we're going to have Y, and we're going to get only one column of my data, which is potability. You can even now go ahead and explore the shape of each one of these variables that you have just created, the shape of X and the shape of Y. Separated by comma, so it is going to give you the dimensions of these two variables. So let's take a look here at the shape of X. I have 3,276 observations, rows of 9 columns. This is the shape of X. And I have here the shape of Y, which I have only 3,276 rows and just one column because it's potability only. That's pretty much it what we did here. We divided our data into X and y. So when I'm going to input the data for the machine learning classifier, I am going to input separately the x and the y. So it will try to learn all the patterns in my data. So I see here that one person liked the split on x and y that Paulo asked. Let's see if anyone here is encountering problems. We now have our second, third, fourth, almost there. And we have the seventh number. Okay, good. All right, now we're going to go here through another step, which is what people refer to as data scaling. For that, I think that I can show you an image that will do this job better. Where is it? Here. Now, I want you to contemplate the image that you see here on screen, and I want any one of you to go ahead, open your mic, and try to explain what you see here. You can do that in English, you can do that in Spanish, it doesn't matter. Let's try to have some participation of you. All right, take a look at the image and let's try to explain what do you see here.
Like we have an apple and a strawberry, but the apple is bigger than the strawberry, and then after the scaling, the apple and the strawberry are the same size.
Okay, that was really good. Let me ask you one thing. What do you think if we compare the apple and the strawberry in their original shape, not after scaling? If I make a comparison, what do you think that is going to happen?
Sorry, can you repeat the question?
Yes, what do you think that is going to happen if I compare the apple and the strawberry before scaling? The big apple with a smaller strawberry.
Well, obviously like if we compare it, the apple it's bigger than the strawberry.
Do you think that is going to be a fair comparison at the end of the day?
No.
That's the thing, right? I'm comparing two things that are different by nature. Let's say that I want to classify the size of images. For sure that one is going to be classified and predicted as bigger than the other, because I know this is a ridiculous example, but what we want to ensure when we're doing data scaling is that we are fair. We are treating each water sample that we have as fair as we can be. Okay, we are not being biased. We don't have a sesgo based on one particular column that might have a greater magnitude in comparison to another column. Now let's go back here to our data and let's show you here the data.describe t. Okay, see here the mean for pH is 7. However, take a look here at the mean for solids. That's 22,000. So the magnitude in these numbers is highly different. Potability doesn't count, okay? We don't want to include this. But see here the mean for turbidity. It is 3.986. So do you think that it is going to be fair if I try to create a predictor that does not have a way to work around with these differences in numbers that are just a representation on the nature that these data were collected. If I bring to the game turbidity that has 3.986 and solids that has 22,000, so probably if you do something like that, you are going to create a model that is going to be biased towards solids, because the magnitude of solids, it is way bigger than all of your other variables. Again, you're not going to be fair. So you just need to find a way to make all of these numbers in the same scale. So when the model is actually performing the analysis, it is treating each column, each row as fair as it can be and in the same numeric system. It's the same thing. We're trying to compare the temperatures in Fahrenheit and Celsius. You see, it doesn't make any sense, right? The scale that these two temperature system goes, it's highly different. So we need to bring them to the same level. That's why we apply data scaling. And again, the same way that we worked with data imputation for handling the missing values, whenever we are applying data scaling, you have tons of different methods that you can scale your data. You can have a 1 to 0 scaling, in which the highest number of your column, the max here, it is always going to be 1, and the minimum of the column, it is always going to be 0, and then you just distribute the other variable, the other values between 1 and 0. You have many different ways for you to do that. One common way that people use here in machine learning is by using another library that we have in Python, another module, which is the standard scaler. That does a pretty good job. I have used it for a long time, and in my opinion, it is one of the best. So for that, you're going to import the standard scaler. So sklearn dot preprocessing import standard scaler.
So
This,
we are like normalizing, or we want to like normalize the variables.
yeah, normalization process, yeah, scaling
Ah,
normalization, yeah.
perfect.
So this is we're going to use the standard scaler dot fit function. This function comes from this library here. So this is a little bit different because we're using the a bigger module, a bigger library, which is the sklearn. Several of the other machine learning things we're going to use, they come from sklearn. So you need to say from sklearn.preprocessing import standard scaler. Now you execute it, and now let's go down here to our data scaling. I copied in the chat here for you the code for you to import, and now we're going to scale. So first you need to create an instance of standard scaler, and now you are going to scale. You're only going to scale the X, okay? The Y, you only have a binary code there, 1 or 0. So there is no point in you scaling the Y. You can only have two possible values here. So only X. So let's get here X. I'm going to create a new X so you can see the difference between the original values and the scaled. Okay, so I'm going to say X scaled equal to scalar dot fit. Oh Jesus, fit transform, because we're doing a fit transformation of X. So instead of updating the values that you already had in X, you are creating a new X, which is X scaled, and you just execute it. And now let's create here another code. Let's see here first our original X. Okay, you remember we did the data imputation. Now we don't have any missing values, but this is not the scale. This is the original. Now, if you go here and you visualize the X scale, you see that now it transformed it. It's not a data frame like a .csv anymore. It is just an array of data, but you see here 3.07 times x raise it to the -3 and so on. So it changed the look and feel. Now all of the 9 different columns that we have, they are in the same scale. They are normalized. So that's how you do it. I'll just wait here a few moments until we make sure that everyone has the data are already scaled. Yeah, you should be able to call your new variable x scaled. It's not mandatory, okay? If you want to just overwrite your existing x that you have here, you can do it. But I think it's always good for us to not to lose information, not to lose data when executing your code. Because let's say that at any point in your code later down the road, you're going to need to refer to the original values that you had on X. Then for you to do that all again, it is going to create you a big problem. So I like to create new variables. This is one of the good practices that people do in programming. But here for this example, it shouldn't cause you any troubles if you just update it. Instead of x scale, you just add x scalar dot fit transform x. So x is updating itself. It's been overwritten. Again, doesn't matter too much. Okay, now we did the data scaling. Now there is going to be here another step for which I'm going to determine it with the text, which is the train and test split. And this is again really important for us to execute it. We're going to first execute a machine learning. We need to divide the data into splits on the train and on the test. I just see here that we have 5 likes on the scale. Is anyone facing any problems? Remember that before actually executing this cell here, you need to go up to the cell that we have all the libraries imported, and you need to add this from sklearn.preprocessing import standard scalar. You add this line here, re-execute this cell, so you included a new one, and now you can make use of the standard scalar functions, which is here. All right, now let me go back here to our images. And now this is the image that I would like you to contemplate and analyze, at least for a few moments. We have all of our data, and we are splitting. This is the verb that we have chosen to use there. We are splitting the data into train and test. This is not one of the, as we did before with the scaling, that I'm going to need you to explain what you're seeing here. This is something more inherent to the actual machine learning itself. Because you see, we are dividing all of our data. You can check the sizes of the rectangles. The bigger rectangles, they are exactly the same size. However, the second rectangle that I have here with the train and test, it is divided into 2. The train and then the test. The train is 80%, the test 20%, 75, 25. Don't know exactly by looking at the sizes here, but it's probably approximate. So why in machine learning we need to divide the data into two sets, the training set and then the test set. So if you remember before, let's go back here, in which I have this explanation. So we have the function side of it, right? We're trying to say that function of x is equal to y. I'm trying to say that a combination of my x variables, it is going to result in a y. So why we need to separate these into train and test? This is actually to grant the capacity of your machine learning to generalize, because I am going to insert the train to my machine learning. It is going to use the training data to create the patterns that it needs to be able to classify, to execute our function here. Remember, this is this is nothing but a function. I'm trying to classify all of these 9 columns into potable or non-potable. So first, I separate a set of my data as training data. The model uses these training data to formulate the patterns, to learn. That's why it is called artificial intelligence, because the model is actually capable of learning without going too deep in the philosophical definition of what is to learn. And then I have the test. So the model, the algorithm, has never looked at these test data that I have here. It formulates its knowledge, its base of knowledge in the training, and then I test the model to see if it runs well or not. This is, to some instance, getting a very simplistic example. Does anyone here remember what was the car that you learned how to drive when you took driving lessons? What was the car?
Standard
Sorry?
and standard.
All right. So if you drive in another car than that, can you drive or not?
Yes.
That's what you expect to happen, right? And this is the same thing that we apply here in our machine learning model. It's not because you were trained in one type, one instance of your data that you're not going to be capable to perform well, to generalize, to execute, to work when you are inserted with new data. So we need to make sure that the model can do this generalization step. So this is what we call train and test. You first train in, let's say 80%, 70% of your whole data, and then you reserve the remaining 80%, sorry, 20%, 25% to test, and you assess how the model performed after that. So if you understood this concept here on train and test, now we're going to divide our data into, again, train and test. For that, we're going to use another library. So go up here from sklearn.model selection, import train test split. Let me copy this code here for you so you can import it. Execute the cell again with the inclusion of the new model. It's ready to go. And now we are going to actually do the split. So train test split, we have here our data. So this is going to be like a long code. We're going to have the X train. and the X test. I'm going to have the Y train, and I'm going to have the, oh, sorry, this is not capital. Y train and Y test. Okay, so these 4 new variables that I am creating here, X train, X test, Y train, Y test, I'm going to have the train test split. The actual data that I'm using to make this split is X scale and Y. And now I need to define the percentage, what I call the test size. You can refer to it as whatever you would like. Again, this number is, you define the number that you want to apply here. Let's get 20%. Okay, so 0.2 is the test size. So that's 20% of the all the data that I have. And this should be enough, but there's another argument that we can include here, which is the random state. You can set any number here, okay? I'm going to set 1, 2, 3. I advise you to do the same because this is going to be a random process, okay? The only thing that you know is that 80% of this value here, it is going to be in the train, and the remaining 20%, it is going to be in the test. When you set the random state, you ensure that every time that you execute it, it is going to have the same random seed. So the same numbers that are the same data rows that are in the train are going to be again when you execute that again, and again. Okay, so this is to ensure the reproducibility of your code. So by executing that, you should be able to have the green indicator here that it went successful. And remember that we used the dot shape function to know the shape of our X and Y. We did it right here. Now we can do the same thing, but for train and test data splits. So let's go here, X train dot shape.
Sorry.
Yep.
I didn't understand very much what does the random state number what is the function of that random state?
Yeah, so you are just ensuring that every time that you execute that, you are going to have the same rows of data included in the train and included in the test. Because if you don't do that, I just specified here that the test size is 20%. Let's, I can even show you that. It's probably going to be easier to understand. So let's execute that, and let's check here the Y test. This is going to be smaller. Okay, so you see here, I executed the Y test and it assigned the value number 2834. This is the actual index of your data. If you open the original spreadsheet, you go here to 2834, you're going to find this value there. However, let's remember, okay, the first number that I have here is 2834. I'm going to execute that again, and I'm going to check Y test again. You see, it changed because the random state, this is based on a random distribution. It just knows that it needs to separate 20% of the whole data to the test. Now, if I go here and I add the random state, this can be any number, okay? You just need to remember to use these number on and on. Let's use here 42, okay? Execute that, check the Y test. 2947. Let's do that again. Remember, when I did without random state, it changed. I execute it again. 2947. It is probably the same thing for you. So can one of you tell me if you do that with the random state of 42 and then you check the Y test, the first number that pops up is 2947? Oh, did I answer your question, by the way? Is that clear now?
Yes, thank you.
Good. I would just like to confirm with one of you if you got the same number as I did here, because it should be the same. If you set the random state to 42.
Yeah, I got the same number.
The same, good, yeah. So that's how you can ensure that you have reproducibility in your code. Very good. All right. You can check as we're talking about the shape, xstring.shape, xtest.shape, and then it has here 2,620 on the train and 656 in the test. When you add random state, you just ensure that these 2,620 are always the same. Okay, they're not going to change when you re-execute the code again. Okay, and now we have the data already prepared and we can start playing around with the machine learning models. So I would just need a confirmation from you if you have the string test split, like if you manage to have the string test split. Okay, we have 5 people who like it. 7. Okay. Good, guys. So now, as I told you, we have all the data already prepared, formatted, normalized, scale, split, everything that you can call it to start checking our machine learning algorithms. And this is going to be something highly, highly variable because you have different machine learning algorithms for different problems. So I have selected here a panel consisting of 4 different algorithms. Remember, all of these algorithms are kind of doing the same thing. You go here to the function, the description of the problem. You are trying to find a way to combine pH, hardness, how do I get out of these? Solids, chloramine, sulfate, and so on, in order to derive 1 or 0. Let's say that low pH, high hardness, high solid, high chloramine, low sulfate, low conductivity, low organic carbon, high trialomethanes, and high turbidity, it is going to characterize potable or non-potable. Okay, but I'm doing that in a very simple way. You need to find the actual cutoff value. So if the pH is higher than that, if the hardness is higher than that, so you see the number of possibilities that you have, it is going to be a function of the number of columns that you have. So something raised to the power of 9, we're talking here about a gigantic number. So that's why we need a robust mathematical method to do so. And the method that is actually being executed by the machine learning algorithm, the idea that it has is the same, is to classify, but it's going to employ different mathematical techniques to do so. So here, in order to keep it simple, this would be one of the stages that we could get one of these algorithms and focus in one tiny aspect of it and talk for hours and do hand calculations on it and updating the weights and doing a lot. But again, we don't have time for that. And I don't think that this is your goal this is actually interesting to you. So we're going to just provide a high-level overview on how each one of these four algorithms that I selected work, and then we're going to plug our data into these algorithms and see how they perform. Okay? So the first two algorithms that I have, they are very similar. Actually, one is one extension of the other, but I would like you to focus here on the image on your left side, which is the decision trees. Okay, this is a very good algorithm for you to start working with artificial intelligence because it is highly understandable by humans. Actually, a lot of our decision-making processes with us humans, they are based on what we call a decision tree. You see here, it's really, really simple for you to understand. You always start reading your tree from the top nodes, and then you keep going down until you reach a leaf node. A leaf node is when you reach it at the end. A decision node is when you're going to ask a question. So, okay, we're trying to predict here basically an animal, all right? I will start in my root node or the top node, the highest one that I have. I am going to see, okay, is the animal short or is the animal tall? Okay, let's say that my animal is tall. All right, does that tall animal have a short neck or a long neck? If the animal that is tall and it has a long neck, it might be a giraffe. However, if the animal has short neck, I need to ask another question. Then we go down another level. So is my tall, short-necked animal have a short or long nose? It has a long nose. That might be an elephant. Now, if the animal has a short nose, you see, is my tall, short-necked, short-nosed animal live on land or in water? If it lives on land, it might be a rhinoceros. If it lives in water, it might be a hippo. So you see, it's really easy to understand the decision process that you have with these because this is something that us humans are pretty used to with doing. A lot of people like to say that medical doctors they apply this process when you are somehow sick and you go to an appointment with your doctor. The doctor will start asking you these questions. Okay, did you eat something that might have caused you these problems, this Montezuma revenge that you might be having today? Yes or no? And then it keeps going and going until you reach a decision node on your tree. Is that clear to you? Did you understand the concept around decision trees? Any questions? Please feel free to ask.
Yeah, I understand it.
It's pretty straightforward, right? Okay, now, still talking about this idea of decision tree, we have what we call a random forest. A random forest, as you can see, a tree, and you have a forest. So a forest is a collective of trees. What you're going to have here is a combination of decision trees, and then you are going to compare the results that you have in each one of your decision trees, and then you're going to have either a majority voting or an averaging of what you have, what was the individual result of each one of the trees, and that is going to be your final result. So this is a more robust implementation of decision trees because you have numbers of, you can specify the number of estimators that you have. Let's say I want to have 100 trees. So actually, for me to have 100 trees, and I wanted to say that the animal that I am predicting is a rhinoceros, I need to have 51, the majority, right? The simple majority, 50 plus 1, 51 trees having said that it might be a rhinoceros. Okay, so as you can see, it is an iterative process on a decision tree that is used to grant independence to each one of them and have more robustness. So decision trees, random forest. Again, these methods are highly complex. You can read an entire book describing you all the equations that are applied in each one of these nodes and how these equations are weighted, how you can have one node having a different weight compared to the other. So this is highly, highly complex. You just got a 2-minute overview on how a random forest work. I don't expect anything from you that actually touches around implementing one of these, designing one of those algorithms by hand. This is not our goal. It's just to provide you an overview on how they work. And you see that at the end, you're just trying to predict f of x equals y. The other two algorithms that we have here, they're probably not going to be as simple as the three basic ones to understand. First one is support vector machines. And the second one, the last one we're going to check is linear regression. So let's start here with support vector machine. You see here that I have the squares and circles, the yellow and the greens. This is not the color of Brazil's flag, okay? I don't know why they did it, but anyways, we have here two classes, maybe potable and non-potable, and I am creating this 2D representation. This is what I call a kernel, in which I am creating dimensional representation of my classes, and I'm trying to find what I call in support vector machine the hyperplane or the decision boundary. And as you can see here, I need to find a way to place the hyperplane in my data that does the best job in separating class A from class B. You were doing something here that is called somehow a technique to reduce the dimensions. This is a simple linear kernel, but you have some other kernels that will have plenty of dimensions, so it wouldn't be possible for you to visualize that in a 2D space on a computer screen. So here you're just mapping your variables, your 9 variables to a 2D representation and trying to find the line that divides between them. And this is called the hyperplane. This is what I call a support vector machine. And here, the last algorithm that we have, this is actually debatable if this is considered machine learning or not. I particularly don't classify that as machine learning. So theoretically and technically, we're going to have 3 machine learning algorithms, and one is statistics-based algorithm, which is linear regression. So you see the mathematics on it are way less complex than we had in the previous algorithms. But I want to show you how do they perform, how they can be compared between themselves, machine learning versus traditional statistics. So you have here the linear regression, and just by looking at information that we have here in the plot, you can basically see what is going on. Check here the labels for the y and the x-axis. Hours of studying in the x versus the probability of passing the exam. You see here that a student that has 3.5 hours of studying will have a higher probability of passing the exam. Again, this is really simple. You're just trying to make a regression of your variables. In that case, the probability of passing the exam and the probability of not passing in the exam, right? So maybe 60-50% should be a good threshold for you to define that. In our water sample example, you just have 9 variables here. Hours of studying, you have like pH, sulfate, chloramine, and so on. So that's pretty much it. Okay, this is again a high-level overview on the 4 algorithms that we're going to check and execute and make sure that we understand them. Again, you can always feel free to go for more details and actually check how these algorithms work. There is a very interesting channel on YouTube. If you like mathematics and machine learning, you can go here to StatQuest. This is a great YouTube channel, StatQuest with Josh Starmer. I'm not going to show the video here, but let's see StatQuest support vector machine. So it's a 20-minute video, part 1 of 3 on a support vector machine. So this guy is incredible. I learn a lot with him. And if you want to actually explore the mathematics, okay, this is highly mathematical, but if you want to see how these algorithms work in a mathematical representation, it's a really good source of information. Let's say that you have here random forest. It probably has a video for random forest as well. So I highly recommend you to take a look at it. Okay, let's go back here to the Colab. And now let's create here a text information, a text cell, sorry, and we're going to have the actual execution of decision trees. What did I do here? Decision trees, random forest, support vector machine, and linear machine. So logistic. All right. There are different ways for us to do that. I could have like a cell of code that does everything all together at once, but I want to go one by one with you, and it's 3:41. Yeah, we have time for it. So let's start with decision trees. Okay. Decision trees. When I add something here in a cell, okay, this is a cell of code that has this hash symbols on it. It is what you call a comment. So this is not executed, okay? So if I had this without the comment symbols, it is going to give an error, a syntax error. But if I just specify here with the hash symbol, it is ignoring that. Okay, so this is not executed code. I also like to use it to comment and have clear delimiters between my code. Okay, so now we're going to have to import all of the models that we need for support vector machine, random forest, decision tree, logistic regression. So let's go up here and let's import the models. Let's start with the first one, which is the decision trees that we started, right? So from sklearn.tree import decision tree classifier. This is the code that you should copy. Just have it here. Don't forget to execute again after you included the new import. sklearn.tree decision tree classifier. So this is the object that we're going to this is the module that we're going to use to create the object of the decision tree classifier. All right, so please import a model, don't forget about it. And now we're going to start our model here. So let's refer to it as decision tree model. And that is going to have an instance of my decision tree classifier that I just imported there. So if you want to have this commented, this is to instance the model, I'm creating an instance of the model. Now you fit the data into the model, and this is probably the most important part of it, but you're going to see this is really simple. So decision tree model dot fit. And what am I going to fit? Remember, we split the data into train and test. I need to get my model to learn the patterns with the trained data, and then I will evaluate how the model worked with the test data. So I'm going to fit the X train and also the Y train. It needs to be separated, X and Y. So you can execute it. And it should give you this symbol here that you have a decision tree classifier. It is already fitted. You can find the documentation for it on scikit-learn. It has some different parameters that you can choose here. But again, we're just using the default parameters because we don't want to go deeper in each one of them. Okay, so I did fit my model. As you can see, this runs pretty much instantly. Okay, we don't have too much data, but if you had more data, sometimes it can take longer to execute. Okay, the model is already fitted with your trained data. So you see, most of the work that we did so far was to actually prepare the data to be predicted. The actual prediction instantly happens. All right, now I can create another variable here. Let's call decision tree predictions. And this is really important for us to see because I'm going to get my decision tree model, and I'm going to now use the function predict. Remember, you use the function fit to fit the data on it, the training data, and now you're going to predict with what type of data? The test, right? But now you're only going to add the X test to it because the Y test has the actual values. So let's execute that, and I'm going to show you how we can interpret that. So let's see here. This is step number 3. Make the predictions. Okay, and this is a variable that we can explore, this decision tree predictions. See, what is that? Decision tree predictions. It is just a bunch of ones and zeros. If you count the length of it, you can check here with the len of your decision tree predictions. It has 656 predictions, right? Either 1 or 0. It predicted 1 for potable, 0 for non-potable. If you check the shape again here, remember the shape of Y test or X test, it has how many data points, how many rows in the data frame? 656. I predicted the same number, 656. You can check the data again, and it will see. You will see here all the ones and zeros. You don't need to count them one by one. But now I would like you to manually compare. Let's go here and get the Y test, because the Y test has actually the values that are real, that were taken from your data. I execute this, and you see the first one is 0. Let's see what the model told me. The first one is 0. Okay, good for the model. The model is right here. The second one is 1. The second one is 0. Bad for the model. It is wrong. The third one, 1. Wrong again. So you see, you can go up to the end. For sure, there is a way for you to get this process in an automated way to actually evaluate the prediction, the actual versus what was predicted. So for that, we're going to import another module, which is from sklearn.metrics, import accuracy score. And this should be enough for us. Oh, sorry, I need to execute that again. Let me get the code here. Execute it. And now we can go down and evaluate our model. I'm going to delete these cells here because we actually don't need them. And now we're going to here number 4, which is evaluate the model. Is the actual versus predicted. So for that, we're going to, let's say, decision 3, accuracy. We're just measuring accuracy here. So this is going to have the library, the function that I've just imported, which is accuracy score of y test and the predictions. Now I'm just comparing, okay, what we did manually. The first one is wrong, the second one is right, the third one is right, and so on. Now you're just having that in an automated way. So predict, now it's decision 3 predictions. Okay, and now you can actually get a new code here and print it. The accuracy of it is 0.73. You can multiply that times 100, and then you get the percentage of it. So 73.47%. Okay, this is the accuracy, the general accuracy of the model. This is basically the capacity of your model to find true positives, true negatives, false positives, false negatives in your whole data set. Oh yeah, that's a good question, yeah, Paulo, to actually check if you achieve the same accuracy. I think that you can specify a random state here. Yeah, you can do the same random state here if you do the 42. Again, these methods, they are they always initiate with a random value. So in order for us to have some reproducibility, it might be interesting for you to add the random state. I'm going to do that again here and see if I achieve the same score. See, 47, now 73.32. Execute that again. 74.69. Execute that again. 73.78. If you add the same random state here, whatever, 1, 2, 3, execute that again. 7393. Execute that again. 7393. Okay, that was a really good point that you mentioned, Paulo. As these models, they are always when you initiate the models, the first run of the algorithm, it is going to set some different weights in the nodes of the trees. So it's always good to add a random state here to add the reproducibility to it. Okay, now we have our first model, which is decision trees. Is everyone with me at the same stage here? We have 2 likes, 3, 4, and we have our good old number 7. All right, so this is, yeah.
I have a question. Sorry.
No, please go ahead.
The 70 93.93, etc. What does that mean? Like the precision, or like how precise is our um, machine learning to predict that something it's in fact potable or non-potable?
Yeah, so this is actually a very good question. Let me get here in the presentation so I can show you that better. There is a good image that represents it well. Let's just find it here. Yeah, this should work. Because yes, let me add the image here. It should be easier for you to understand. Okay, so we also need to get here a confusion matrix. Let me try to get one. Good here. I thought we wouldn't have time for that, but yeah, if you have the question, it's actually important for us to go there. And let's get the matrix here. Okay, so what we're doing here is that we are evaluating what we call a binary classification, potable, non-potable. The way that we do that is by calculating what we call a confusion matrix. As you can see in my confusion matrix, I have the actual, which is the actual labels of the data, potable, non-potable. And here you have what was predicted, potable, non-potable. So these, let me get something here. Do I have the laser pointer? No, but anyway, probably this. How do I get this out here? So these two here are the actual, and the other two are the predicted ones. So the way that we measure that is that we want to have instances that are actual dogs or potable and are predicted as dogs potable. These are what we call the true positives. And for the negative examples, the water samples that are not potable, you want them, you know that they are not dogs, not potable, and you want your model to tell you that they are not potable. These are the true negatives. So the two blacks that I have here, this one for not dog and this one for not dog, this is the error, the true, the false positives and the false negatives. The first one that I have here, the not dog. So this is not a dog that was classified as a dog. So this is a mistake. And here I have a dog, because it's an actual dog that was classified as not being a dog. So this is why it's called the confusion matrix, okay? Because it is a bit confusing. You need to understand this relationship between the four classes that you have here. But basically, in this matrix, what you have is true positives, true negatives, false positives, and false. Let's do it differently. So true positives, dogs that were predicted as dogs. Now I have here the false negatives, which are dogs that were predicted as not being dogs. This is why it is a false negative. It is a dog, and it was predicted as not being a dog. The water is potable, but it was predicted as not being potable. Now, we have here the opposite, the false positives, because this is not a dog, but it was predicted as a dog. This water sample is not potable, but it was predicted as potable. So it is an error. It is a false positive. And then at the end, you have the true negatives. And this is good. This is when you are correct. It is not potable, and it was also predicted as not potable. So then you have your performance metrics. You have accuracy, which is true positives plus true negatives divided by all true positives, true negatives, false positives, false negatives. So this is the accuracy score that I have just showed you before that we calculated. You are basically, with the accuracy, you are measuring the overall capacity of your model to identify true positives and true negatives. If you see here the way that this equation is being constructed, the more false positives and the more false negatives that I have, it is going to negatively impact the balance here in the numerator of this division, right? So these true positives and true negatives, they repeat here. So if I have 0 false positives and if I have 0 false negatives, it is going to be the same number divided by the same number, which is going to be 1, and then is going to be the 100%. However, if I keep adding false positives, if I keep adding false negatives, it is going to disrupt this balance, and I am actually dividing one number, and its denominator, it is going to be bigger than the numerator, which is going to impact negatively, and this is going to cause the accuracy score to be lower than 1. If you do the calculation here, we have 8 divided by 10, right? 8 divided by 10. So this is going to be your accuracy score. So that's what we are measuring here. There are other metrics that you use as well, precision, sensitivity, specificity, F1 score. There are different metrics that you use here to calculate the performance of your binary prediction system, your machine learning system. And again, each one of these metrics, it is going to do something. One, it only calculates among the positively predicted class, only calculates among the negatively predicted classes. I wanted to bring accuracy here for you because it encompasses everything. So sometimes if you are doing something on machine learning and you see that the accuracy is not good, forget about it. Okay, just go for the next algorithm. Just go for another classifier, because if the accuracy is not good, there's probably nothing much left for you to do. All right. I see here that Paulo had a terminology alert.
Yeah, because the problem is that between English and Spanish, there's a bit of a misunderstanding. So we measured 73% was the accuracy, which in Spanish we call precision. But in
Okay.
English, sorry, precision. But in English, for the machine learning, precision is not the same as precision. Precision is, as you said, the proportion of positive predictions that are actually correct.
Okay.
And in
That's fine.
Spanish, we call that, I believe, is sensibilidad.
Okay, that's fine. Yeah, so yeah, that will be a difference in the languages. Yeah. So
Yeah.
in English we have the precision, which in that case for you is different. And as Paulo said, this is just the proportion of the classes that were predicted as being positive. So you want to get many true positives correctly predicted and as few false positives as you can. So this is the the precision. It's a bit confusing to to figure out the way that these work, but yeah. Thank you, Paulo, for the clarification. I know that this was a long explanation. I wasn't planning to include this in the class. I was afraid that we might not have enough time for it, but I'm really happy that I had the opportunity to clarify that, and I couldn't get the name of the our colleague that answered the question, but did I make that clearer for you now?
Yeah, it was excellent. Thank you.
Okay, perfect, perfect. Don't get fooled by its name, okay? Confusion matrix, but it's not that confusion, and we can understand it. All right. So this value that you see here, that I just multiplied by 100 to get in a percentage uh, format, but this will never be higher than 1, okay? Because on what we check, the way that we build those equations, the maximum is always 1. So this is the accuracy of our decision tree classifier. Now I'm going to copy all of that, and we are going to have a different model. Let's now work with the random forest. So I'm going to go up here from sklearn. This is the ensemble. Import random forest classifier. Get this line of code here for you in case you need it. And it's here in the chat. I execute it. And let's go down. And now we're going to change it here. Let's call random forest model. It is going to be a random forest classifier, random state. I use it 1, 2, 3. Yeah. You execute it. Now I need to fit it. I just changed the name of the model. I make the predictions. I just change the name of the model. And I have now the random forest accuracy. A lot of copy and paste. Oh, sorry. This is random forest predictions, not model. And there we go. And then at the end, we see random forest accuracy. Let's multiply by 100. This is executing. Oh, as you can see here, 81.09%, which is considerably better than what we had in the decision tree. Yeah, that's 73 to 81. That's a good improvement. I like it, the results of these models. So as you can see, 81. If you add the random state here, it is going to be reproducible. So anytime that you execute it again, it is going to get you the same value. Random forest decision trees. Okay, so I'm going to wait and see if you got the same values as we did here for random forest, and then we will go for the next models. There will be a challenge for you on that board. So please reply to Paulo's question here. If you had issues, don't hesitate in typing in the chat, opening your mic. We're here to help. I have one like here. If you're having problems, please let us know. 2, that's good. All right, guys. So now the remaining 2 models that we have, sklearn, sorry, SVM, and logistic regression. I am not going to execute that with you. I'm going to get you the imports here, and I want you to execute these models on your own. Let's use a random state of 1, 2, 3, and then we can see the results that you are obtaining. Okay? You import, and you just need to change the names here as we did before. All right? So the support vector machine, it is going to be the SVC classifier, and the logistic regression is going to be logistic regression. Let's have this small challenge to you and see if you can execute these 2 remaining models on your own, and then we can compare. Yeah, thank you, Paulo. If you're having problem, if you're going to have a problem here, you're going to have a problem in this particular part in which you are instancing, creating the instance for the model. So for the SVM, you use the SVC or SVC, and then you specify the random state. And then for the logistic regression, and that will be it. The rest, you just change the names here of the model itself and the predictions and the accuracy. Okay. Well, it might be the case if you're having a problem with the SVC, you might need to specify the kernel. You can try without, but now I'm not sure if it works without you specifying a kernel. But you can set it to linear. That won't be a problem. So if you find a problem in SVC, that's for support vector classifier, then it might not work with the random state only. You might want to add the kernel, which is, you can use a linear. Let me see if it works. Did I import it? Oh, I did import it. Sure that it's not going to work. Yeah, you don't need to specify the kernel, so that's fine. All right, we have here one result for accuracy. That's a 69. That's bad. Worse than decision trees. Generally, support vector machines are good. Let's go here. SVM model, SVC, SVM model, SVM. SVM predictions and SVM accuracy. Yeah, 69.965. Oh, impressive. Maybe if you change the kernel, it can get you a better result. If you use like a polynomial kernel, let's see. Oh, even more, 63. That's the RBF is a good one. Linear. Yeah. The problem is SVM, so you can conclude that SVM is not doing a good job in trying to separate this data. And we also have here Liam, who's got results for logistic regression, and it's even worse. Let's get mine here for logistic regression. So just call it LR, just regression, LR model, LR model, LR predictions. Oh. Yeah, 62.804. Yeah, so you can conclude that the three Bayesian models are doing a better job in classifying our data. Oh, and you might how was 81% for random forest? You might want to say that 80% is not good, but I would stick with it. Okay, wouldn't be too bad. The 100% in machine learning is a fantasy, all right? You're hardly ever going to get the 100%. You're going to get 99.98, 99.99. If you get 100, be careful because there might be some problems with your data. But yeah, it looks like our random, yeah, if decision trees are worse than are better than random forest, and I would be worried because as we check it on the fundamentals of random forest, it combines multiple decision trees. So not saying that it's always like that, but in most of the situations, random forests are going to be better than decision trees. Okay, I'd like to have a plot here with you so we can compare all of these accuracies together. Is there anyone who is still working on the implementation of the last two models? I see here that maybe 4 or 5 people. Okay, I think that we can go ahead. So as you can see, it wasn't out of nowhere that I created these accuracy variables here. The logistic regression accuracy, the SVM accuracy, the random forest, and decision trees, because we're going to try to consolidate now and visualize all of these results together. So let's get here, visualize accuracy results. Let's try to have a plot for it. I think that it will help you. But first of all, I want to use this information here to create a data frame, like a CSV, as we have been working with so far. So let's get here models, accuracies. And we're going to get a data frame. So pd.data frame. Yeah, so I have
Sorry,
decision.
I
Yeah.
have a question. Is there or are they any other situation where like support vector machine or logistic regression better models than the decision trees or random forest?
Yeah. Logistic regression, it's not even a machine learning application. Okay, so for logistic regression, this is basically our control. I just wanted to show you how machine learning can do better than these traditional statistical methods. But support vector machine, yeah, it all depends on the nature of your data that you have. For instance, support vector machine sometimes does a good job in classifying data that is not scaled. Actually, one of the ideas of support vector machine is to have non-scaled data. So that might be one occasion that you can apply it and get a better score. It's not that you're always going to have the random forest the best, and before that you're going to have decision trees, and before that support vector machines. The data sets that you have are going to basically dictate the models that you are going to apply. Whenever I get a data set that I want to predict something with it, I like to apply these panels of models just so I can see and have an idea on which model is performing the best. But here we can see that our data is leaning towards a tree-based model, which is decision tree, random forest. We could even go further and apply a better implementation and faster implementation than random forest, which is XGBoost. That would be probably the most advanced implementation of a tree-based model for classifying. Actually, XGBoost is a model that I like to use a lot. I just didn't bring it here today because the mathematical concept around XGBoost is a bit hard for us to explain. And there's the whole gradient descending that I would need a lot of time for it. And then I thought about just living with random forest and decision trees because they are more digestible. But it depends on the data. Honestly, I think it's good for you to get your data and apply different models on it, so you can just have this initial look on how they're going to work. And as you can see, the computational cost here for us to execute these four models, it is really simple. We don't. It took a few instances for it to run the models. That's pretty much it. I see here that we have a comment from Paulo saying that support vector machines are good for filtering spam email. That's good. That's interesting. Yes. There are lots of applications that one model is better than the other. So if there was just one model that was the best, they wouldn't even bother in creating other algorithms, other models. So it all depends on the data. But it's good when you get some new data, try to apply different models, and not only different models, but models different in nature. Tree-based models, support vector machine, that is the hyperplane-based models, even statistical models such as logistic regression, and so on. Good. Did I answer your question?
Yes, thank you.
Okay, good. All right. Now I am just creating here a data frame called models accuracies, which has, let me copy the code here for you in case if you need it. So let's execute it and let's just see how it looks. It will just look like a data frame. Beautiful data frame with two columns for rows, and that's pretty much it. And now, why I wanted to create a data frame with that, because we're going to plot this different models, and you're going to see that it will be easier to plot when we already have a pandas data frame, and we can benefit from all the code that we can execute directly on the data frame instead of having to specify all the columns, the x and the y-axis. So let's go here, plt.figure, fixed size, random, the fold 10.6. Can we get a bar plot, I think? What am I missing here? Oh, there's another parenthesis. Can get a bar plot. So a bar plot is going to have the accuracy, and it is going to have the model. So in the x, we can have the model exactly how it appears in the data frame here. Okay, so you need to get it exactly like this. And then the y, it is going to have the accuracy. This is coming from my data, which is models accuracies. And yeah, that should be it. We can now get the plt.show. Let's just execute that. It will be a simple plot, a bar plot. And there we go. See, the random forest is the highest, 180, and we have decision tree, and you have SVM and logistic regression. Again, you could customize all of these different colors, title, add a grid lines, grid markers. We're not going to do that. This is only for aesthetics. There is one final segment that I would like to explore here with you today. We still have like 30 minutes, so we're going to tackle these, and that would be all of what we have planned. Does anyone have any questions so far? With these, we basically concluded at least the application of the machine learning. There will be another step that we're going to use now, but if you have any questions so far, please feel free to ask. No questions, I'll take that as a no. Now we're going to have here something that we call model interpretability. And this is something that you might be wondering. You see, we know that random forest was the model that made the best predictions, but that's it. We just know that it wasn't 81%, and that's it. We don't have much information about how all of our 4 models here are actually making their predictions. This is why in machine learning there is an important step that in the past people didn't pay too much attention on it, I would say, because you see, you have a model and it does really well in classifying your data, that you just don't want to know how it is executing, how it is, why it is so good or why it is so bad. And you see, the models were there, they were working, and that's it. But then people started to develop some methods to actually map the decision-making process of these models. And I've been hammering these here with you on and on, that the mathematical complexity of these models is not something that is easily understood, especially if you try to translate that in a human readable format. We have here our classification taking place with 9 columns. So everything needs to be raised to the power of 9, which is definitely going to be a lot. Imagine you manually trying to find the relationship between 9 columns that are continuals. Numbers go up and down. It's not a predetermined class. And you see these numbers need to find a way to classify zeros and ones. This is going to be really difficult. Like your potability, sorry, your pH needs to be higher than 2 but lower than 2.5, and then your um, hardness needs to be higher than 7 but not higher than 9, something like that. And then you need to test all of these different combinations. And as you have lots of columns, the problems are raised to the power of 9. So you can just wonder how mathematically complex it is to do so. Here we haven't actually realized that in practice, because our data set is quite small with 3,200 rows and observations, but sometimes you get something with like 100,000, a million, and then you can see that the model is going to take a while to execute, maybe 10 minutes, depending on the model. It can take up to days to train the model. So you need to have that in mind. But again, the whole idea that I want to the message I want to transmit here to you is that learning how these models are making their decisions is not that trivial. That's why, let's go back here to our slides. Sometimes AI models and machine learning models, they are labeled as black box models. You see, you have the picture, the image here. It is fed into the model, and the model just says, okay, that's an insect. At start, you might be really happy. So, yeah, okay, I have my model. The model is working well. It is correct. Yeah, that is an insect. Model is correct 90% of the times. That's really good. But if you want to expand on that, at some point you will need to ask the question of why this model has said this image is an insect. And this is what you call opening the black box to learn the decision pattern of your AI. And as you can see here, now it is telling you, okay, this is an insect because it has 6 legs. And okay, now you can actually see that which is the column, which is the variable that was considered by the machine learning classifier when it made these decisions. And this is adding interpretability to your model. So the model was already correct. You just now want to know why and what makes it correct when it is correct, and maybe even on the negative side, if your model is not working fine, maybe you have one variable that is getting a lot of attention, and that variable is not a good representative of your data. There is a clear exercise of that. I don't know here of you who have pets in your homes, but a couple of years ago, I was working here with some students on a project, and we did uh, something like this. We worked with an image classifier, and it was an image classifier for cats and dogs. I wanted to start with something really, really simple. I had these students that have just joined at our lab, and I wanted them to work on that. So I got them to collect pictures on the internet and cats and dogs, and then we trained our models. Just a disclaimer, you might be wondering that the idea of creating a classifier that classifies images is totally different from what we have seen here today. You see, okay, this is something I will never be able to do. Uh, Not that bad, because you will do a big, lengthy data pre-processing process, and at the end, your image is going to look like this, a matrix. with pixels that are colored or not, but it is still data. Most of these instances, generally these image classifiers, they apply a technique that is called a convolution, the convolutional neural networks, and then for that you are basically transforming the pixel map of an image. You run that through a convolutional layer, and then you have a matrix of data, the same way that we had here. Okay, so this is not that far from what we have been doing up until now. But yeah, then I had the model. I got the students. They did a good job. They got like 3,000 pictures of dogs and 3,000 pictures of cats, and then we started to test the model. And once I entered the picture of a husky, and the model was doing really well. Like this is a cat, this is a dog, and so on and so on. And then once I don't know why, but I just entered the picture of a husky to the model, and the model started saying cat. And then I got the picture of another husky, and the model said cat, and another one, and the model said cat. Does anyone have any idea of why? Then I wanted to discover how, the model, why the model is getting all of these husky images. Maybe the students didn't get any pictures of a husky in the training data, so it never learned that was actually a dog. But does anyone have any idea of why it was classified as cat instead of a dog?
Maybe because of its ears that are okay. Yeah.
Precisely it. If you see here, let me get another dog, like a golden retriever. You see here the ears are facing down, and then you get here a picture of a cat. I don't know all cats that exist out there. Okay, this one doesn't have the pointy ears, but I would say that 98% of the cats at least have pointy ears. And then why only the husky was being classified as a cat? And then we try to, this is the process that you do, opening the black box and understand why the model said what it said. So in those images that we had, we understood that the model was giving a lot of attention to the ears. So it was isolating the ear in the image, and it was like the first variable that the model considered to make its prediction. So it was really funny. So as I told you, you also want to use that when your model is wrong and you want to know why it is wrong, because generally it's not going to be a problem on the model, it's going to be a problem in your data. Maybe we should find some data of some huskies to actually tell the model, okay, you have dogs that have pointy ears. And that's fine. You also need to learn from these. So this process that we call opening the black box of AI tools. Any questions so far? No. All right. So we're going to execute here. I'm going to keep it really simple. You guys might be tired. You're listening to me for a long time right now. So for that, we're going to install another package. But this package, it's called SHAP. I know that Paulo works a lot with SHAP. He's really good at it. However, if you just go here and try to import it, it's called SHAP. It is not going to work. If you want more details on SHAP, there's the website here on SHAP, which is called Shapley Addictive Explanations, which basically explain the output of any machine learning model. This is what is good about it. It's model agnostic. So any model, random forest, machine learning, random forest, XGBoost, support vector machine, you can just apply SHAP on it. So if you want to explore the documentation of it, the website that I have here is really good. There are also some videos on YouTube explaining it. So if you just try to import SHAP, it is not going to work. I would say that this is a limitation on Google Colab. So you first need to install in this computer here of yours that is running on Google, and you install SHAP. Pip, that stands for the Python install package. Pip install SHAP. And this should work. It probably will take some time because it needs to download the package. So you'll see that lots of things are happening here. It downloads, it installs, and so on. And at the end, if it was successfully installed, you should see something like this. There are some dependency packages as well, this slicer. So we needed to install this package in order for Shapley to run correctly. And now if you do the import, you can go up there and import it right here. But as this is something separate from the main content of the workshop, I'll just have it here. And now if you go here, import SHAP, now it should work. Yeah, now it executed. Is everyone okay with installing SHAP? See that Paulo is probably asking here if you're good with it. Anyone?
We saw many thumbs up as a reaction, so I think we can proceed.
Okay, good. Right. So now we imported SHAP, and now we're going to the same thing, when you were defining your models, the first thing that you had to do is to create an instance of your model. And here it is going to be the same thing. So we can call it an explainer. This is generally how people refer to these variables. And we're going to get SHAP.tree explainer. Remember when we checked it here, the documentation, it said that explain the output of any machine learning model. This is true, but it is good for us that the model that we selected to be the best here, it is a tree-based model, random forest, because SHAP itself is really, really slow to execute, because it needs to do a lengthy process to test all the different combinations on the variables that you have. Because what we want here, we want the model, the random forest model, to tell us which of the 9 variables that it considered to be the most important one when it made its predictions. So as we have 9 variables, you need to basically uh, make these tests for a factorial of 9 until you have the variables isolated, and you do these over and over and over. So this is very, very complex and computationally intensive. Depending on the model that you are applying SHAP, it takes days for it to execute. It is really, really slow. However, if you're working with tree-based models, then SHAP has the tree explainer, which is a different instance of a SHAP explainer, which is really faster. So that was really good that our model here was a random forest. So we create a tree explainer from our, what is the name of the model? Random forest model. That's an easy name. We create a tree explainer of the random forest model. I'll execute these separately. Okay, this is going to be quite fast. And now what we need is the values of SHAP. So we already defined the explainer before, that is this explainer here based on our random forest, and we are getting the shape values of some of our data. You can get the train data, you can get the test data. In that case, I'm going to get the test because I just want to see something here. Yeah, this might take a while to execute, and it's the test. If you get the train, it will take even longer. And as all of you are in different machines, I don't want to be desynchronize it with you all. See, this is still executing. So even by being a tree explainer that tends to be faster, it is still taking some time. You see, we're not used to these, this 23 seconds of a cell taking to execute. All of the other examples that we had, they were pretty much instantly so far. And if you try to explain the X terrain, it is going to take even longer. But so that's why I would always stick to the test. But again, you can do in both, and it's not going to be a problem. So just go ahead and execute it. I'm going to kill this and do for the test again because I'm afraid that this will take a while. And now it's executing, I won't be able to stop it. Anyways. Did anyone want to say anything? I saw an open mic there. Yeah, this is really slow, but we're going to start exploring it in a second. Don't do that, okay? Don't go in the train. Just run the explainer in the X test. 58 seconds. Okay, this was the keyboard interrupt that I had here. Let's now do on the test again. It will take those other 23 seconds if I am correct. Okay, now it's good. All right, now you have here this newly created variable. Before we actually have a shape summary plot on the importance of our variables, I want you to understand and try to wrap your mind around what this is actually doing. So let's check here shape values. Let's just check the shape of it. And you see here that I know that in the test I had 656 observations. I had 9 columns, but now if you see here the X test dot shape, you see it has 2 dimensions, 565 by 9. The shape has 565 by 9 by 2. So this is even hard for you to visualize because this is a 3D matrix. And does anyone have any idea of why the shape values is adding a new dimension? So it has the same number of observations, the same number of columns, but there's a third dimension here that is doubled. Does anyone have any idea? How many classes we have in our data? Potable and non-potable, right? So it creates one observation for all the ones that are potable and all the ones that are not potable, even the wrong ones. Because as I told you, see the problem with the Husky, even when you are wrong, you need to know why you're wrong. And the way that you can do that is by taking a look at these shape values. So that's how the shape values looks like after you already map it and use it some data to explain it. Now, generally what people do, they only get the positive classes. So I want to isolate these with you. So shape values potable. So we can get the shape values. We get all, oh, sorry, it's a square. So we get all observations, all columns, and we only get the class 1. And now, if you see the shape of this new variable that we obtained here, you lose that third dimension now. So now we only isolated the positive classes on our shape values. And now you can use these to plot and see how this is going to look. So let's get here a shape.summary plot. We're going to have 2 arguments here, which is shape values potable, and you are also going to get the X test, which is the origin that this data is coming from, right? And you execute that, you should have your shape summary plot. And this is really interesting. So before we start explaining the plot, and this will be basically our last step today, just want to make sure that we are all good here. Everyone managed to get the summary plot. The steps that you need to create it are these 4 cells that you have on the screen right now. Import, explainer, isolate the class potable, and the plot itself. We have 4 people that generated it. Five people. Six people. Okay, that sounds 7 people. Yeah, we're good. All right. Now, as you can see here, this plot is really interesting because I would like you to focus on the y-axis here, the left side on the y-axis of the plot. This is a 3-dimensional plot, so there is a lot going on here. But I wanted to focus first on here the features. So you see here that it is creating an order of the features, which are exactly the columns that we have in our data. The first one that appears here, it is the most important feature that SHAP is identifying in our model. So feature number 4, column number 4, followed by 0, followed by 1, followed by 2, followed by 3, and the last one is the feature number 8. As you see here, the way that the data is distributed, it changes a lot from these features. Let me just get the data back here to you so you can actually explore it. Let's just execute it. Okay, so in Python, we always start at 0. So feature 0, feature 1, feature 2, feature 3, feature 4. So the most important feature that is being mapped here by SHAP is actually the number of the value of sulfates. So this is by far, not by far, as you can see, the distribution here on features here and pH is also good if you quantify the feature importance of it. So as you can see that these features, they will have an impact on the model output. As you can see, the impact goes higher than if you compare here with feature 8, which is the last one, turbidity. So in that case, turbidity, it doesn't matter too much for us, at least for the model. Okay, it's sometimes the model is not considering the feature. It doesn't mean that the feature is not important, at least chemically, environmentally, biologically, whatever. It's just that particularly here in this particular application, in this instance of the model, is not important. And you see here, sulfates, it is the most important. And then you can actually check the color of the points here, because you see each of this dots that you have here, they represent one data point, one row of your data. So as you see here, if you have the color here is purple, right? You go to the far right of the plot, because these are the ones that are having the most impact here in your x-axis on the shape value, the impact on model output. So you have here the color purple, and this is the value of the feature. You see, you have the purple, which is here in the middle. You can get here the data.describe t, and let's go here to sulfate. You see here that the minimum value is 129, the maximum is 481, the average is 333. So when I have a mid-range value on the feature sulfate, which should be closer to the mean, 333, these are the ones that are having an impact on the model. And now we need to consider the class that we isolated to map here. Which class is this? Potable. So with that, we can conclude that potable water samples, the ones that have a mid-range value on their sulfates, they're going to have a positive impact. So if you go and explore the data itself, you will see that lots of instances in which the sulfate was mid-range, maybe on the 50%, on the median that you have here. These are contributing to a class being assigned as positive, in this case, potable. If you get here to feature 1, you see that the situation is different. Here, feature 1 is, forgot about it, hardness, sorry, hardness. So pH is 0, hardness is 1. You see that you have these blue dots here, and this is low. So it means that the model considered a low value on hardness for it to consider, for it to predict one water sample as being potable. I honestly wouldn't be the best person to tell you what is the chemical, biological rationale around it. Does anyone have any idea why low value on hardness should contribute to water being potable? Paulo, you explained the data before. Maybe you have an idea.
It may be because water that is hard, it means that it was in contact with minerals, and therefore it might be contaminated with metals, or it could also be related to the interaction with pH. So there are several interactions that could explain it. It's quite a complex matter, but I think it hardness is more of a marker of the quality of the source of the water.
Okay, I see, I understand. You see, that's why the domain knowledge, actually knowing the problem, knowing your data is really important. We run the whole machine learning execution pretty swiftly, wasn't a problem at all. You actually need to understand the data. So I'm going to stop sharing my screen here with you. Let me get here. I see that we have a question here. I raise a hand.
Yeah, it was me. I wanted to ask, what does negative shape value means. It's like it has it determine that that's not it's a non-potable in water or what?
That's a good question. Let me get the I'm in the wrong screen, sorry. Let me just get the plot here again. Yeah. So, Jose, when you mean negative Shep value, you mean negative by the blue color here or negative here on the x-axis?
On the axis.
Yeah, in that case, it means that this particular value doesn't have too much of an impact for your model to assign its predictions. Okay, so this is quite interesting because you also see here that a lot of instances in which the sulfate was also mid-range moderate, the SHEP didn't consider them to actually classify. But as you can see, when you start going right, you see that you have lots of red here, some blue, some red. So uh, again, it's not always that you're going to find some logical rationale behind it, because this is just why the model is making what is making actually. So you need to consider that sometimes it is just an artifact that the model ended up using. It's not all the times that you're going to have a real world explanation of it.
Okay, I get it. Thank you.
Do we have more questions here in the chat? There are some other ways that you can apply SHEP. This is we're doing the general for the whole model. But if you want, you can isolate one particular water sample. Let's say I want water sample number 218. And then you can isolate that particular one and just check the SHAP force plot, as they call, in how this observation was treated, and if it was right or wrong, and so on. SHAP is a really powerful library. I just gave you a glimpse today on how it worked, but again, it's really powerful. Do we have more questions? I don't think so. All right, so we are technically already out of time. We're supposed to have finished 2 minutes before. So as I told you, it's a lot to cover. I hope that you at least understood in this general idea, what machine learning is and how to execute it, and also demystifying that this is complicated, that it's not easy to understand. This is quantum physics or something like it. Uh, Pay a lot of attention on the data itself, understand the data, because machine learning, you will find a way to execute it. That same saying that I told you from that book before, if you have a team of mid-range engineers with access to very good data, you can probably do better than a team of the brightest machine learning engineers in the world with limited access to data. So if there's one message that I'd like to transmit to you today, especially as you guys are from different areas, I don't see that we have any one here that is from computer science itself. So don't see that as an inhibitor for you not to try to adventure and learn from these. I hope that both Paulo and I delivered some of what you were expecting, and again, it was a huge pleasure for me to be in here with you. You have my contact, so if you at any time need anything else, just let us know. Yeah, we'll be happy to follow up on anything.
Thank you so much. It was very interesting.
Yeah,
Thank you.
it was very well explained. I understood almost everything. Of course, there are something that because of the nature of the I don't know, the subject, it's difficult to understand, but um like you said, on a high level overview, it was good. It was good.
That's good. Thank you. Thank you. I'm really happy that you found it useful, and yeah, hopefully this will be just the beginning for you guys to venture more in machine learning. I was thinking about sharing the notebook with you. I can do that, but all the things that we covered here in class is present in my reference notebook, so I can share it here with you just in case if you missed anything. But again, all the things that we check it in class, you already have access to. I can send you by email later. So yeah, if you gotta go, that's totally fine. And here's the link for the notebook that I use it as reference. Good. I'm really happy that it was helpful. Hopefully that sparked that idea for you, and at least getting this overview